everyone. Welcome to our Module 3. This module will give you the most important lessons and will demystify the most important knowledge that most of food safety professionals must understand. You stay with me. In the first 4 minutes, you will understand why I'm saying that, and throughout this course, I will show you all the evidences that are applicable globally. Let me not give you much of the introduction. Let's proceed. How food safety really feel. Let's start first by understanding the patterns behind 2024's record-breaking recall crisis. In 2024, in US, the USA experienced 241 FDA food recalls. That is an 8% increase from 2023. The boar's head listeria outbreak alone killed 10 people and hospitalized 59 across 19 states, forcing the closure of an entire production facility at the time. But here's what the headlines always miss everywhere where such crises happen around the globe, and we will resolve that as we progress. Every major failure, every major failure was predictable. The warning signs existed months, sometimes years before catastrophe struck in our industry. These patterns repeats itself globally in every food crisis. And let me give you just few examples where these patterns that we are going to learn today repeat themselves and how to prevent them. We will progress to show you how to prevent them. First, those patterns repeat themselves in the incident of Jensen Farm in 2011 in USA, where 33 people died from the cantaloupe. And then the same patterns repeated themselves in the crisis of Peanut Corporation of America, USA, in 2009, where 9 people died and criminal convictions happened. The same patterns repeated themselves in Bluebell Creameries in USA in 2015. Again, it resulted in 3 deaths and company nearly bankrupted. The same pattern repeated themselves in Fonterra in New Zealand in 2013. That crisis resulted in global recall and cost the company around 19 million in direct cost. And the same pattern again repeated themselves in the crisis of Cadbury in UK 2006, where 1,100 fall sick and it cost company 20 million pound that time. Now, this module reveals the 5 universal patterns that explain why food safety fails across all these cases, regardless of country, company size, or food sector. More importantly, you will learn how to detect these patterns before they cause harm. This module will change how you think about food safety failure forever. You will understand why the same failure patterns repeat across industries, countries, and decades, and how to design systems that actually prevent them. Welcome again to our Module 3 of how food safety recall fails and failure is in design in, and we will explore that. This module is presented to you by Walball, founder of QHSE 360.org. First, let's address the core question that changed everything. This module, the focus or the first address question that we want to, uh, to highlight is the question that haunt every food safety professionals after any major incident happened ask the following question. If anyone involved wanted food to be safe, how did it still fail? This is not a rhetorical question. It is the key to understanding modern food system failure. The uncomfortable truths are the following. First, the board's Hague facility had USDA inspectors on site. They had HACCP plans and they had monitoring records. Yet, 10 people died. Then, in Peanut Corporation of America, they had inspectors and third party audits and documented procedures. But yet, 9 people died. And then in Jensen Farms, had audits, they had certification and established processes, but yet 33 people died. Also, in Blue Bell had over 100 years of operations experience. They have a strong reputation and they have excellent quality system according to them, but yet 3 people died. These patterns repeat across industries, countries, and company size. Certified facilities with documented controls still experience catastrophic failure. So, understanding why require us to look beyond individual mistakes to the systematic patterns that enable failures. What you will learn here in this module, you will learn the 5 universal failure patterns that repeat across all food systems. You will learn why these patterns emerge even in certified and audited facilities. And you will learn how to detect warning signs before they become crisis. And also, you will learn practical tools for interrupting failure patterns in your operations. Now, let's first clarify what this module will do and will not do. So before we proceed, we must be explicitly clear about what this module will and will not do. The following will not do. This module will not do incident storytelling. We will not count specific food safety incidents or assign blame to companies or individuals. Also, we will not do the blame analysis. We will not search for who was at fault or what rules were broken. Also, we will not do the root cause template. We will not provide generic checklists or lesson learned cliche. No. This is what we will do. First, we will do a study of predictable failure patterns. We will do an examination of how modern food systems create the conditions for failure across sectors, countries, and scales. Also, we will do a systematic analysis by understanding how failure emerges from systems design, not individual actions. And also, we will do prevention framework by learning to recognize and interrupting failures patterns before they cause harm. This reframing is essential because we are studying failure patterns to prevent them. We are not studying failure patterns to assign blame or create fear. Now, let's explore the fundamental myth and demystify this myth. The most dangerous myth in food safety. Before we can understand how food safety really fails, we must break the most persistent and dangerous myth in our industry. The myth or myth, okay, is the following. People will say, or The myth generally is quoted as, if I want food to be safe and I follow the requirements, food will be safe. This is dangerous because it's almost true, but it's a myth. But because it's almost true, it makes it believable, and it contains three reasonable assumptions. It assumes that, first, good intentions matter. It assumes that following requirements creates safety, and it assumes that individual efforts determine outcomes. Why this myth persists? It's comforting. It gives us control. It makes failure someone else's problem. It makes the failure the result of bad actors or lazy workers. So, why this myth is dangerous? Because it's fundamentally wrong about how modern food safety works. The evidence why this is wrong: one, the Peanut Corporation of America had the following. They have documented HACCP plans reviewed by regulators. They had regular inspections by state and federal authorities. They had third party audit certifications. And they had established monitoring and testing procedures. Yet, over 2 years period, the following happened. 12 separate salmonella positive tests were documented. Products were shipped before test results were received. Management instructed staff to ship contaminated products. And also, as a result, 9 people died and 714 were sickened. Everyone showed up to work, procedures existed, documentation was maintained, yet catastrophic failure occurred. The reality is the following. In complex systems, good intentions and documented compliance are necessary but not sufficient. Failure emerges from patterns in how systems operate under pressure, and patterns that exist regardless of individual motivation or documented control. So, understanding these patterns is the only path to preventing them. Now, let's explore the five universal patterns. We will have an overview and then we will go into details. Across industries, countries, and scales, food safety failure follows five predictable patterns. These patterns are universal because they emerge from the fundamental nature of how modern food systems operate under commercial pressure. So, why these patterns matter, you ask? Understanding these patterns transform how approach how we can approach the food safety, and instead of reacting to individual incidents, after we understand these patterns, you can detect and interrupt systematic vulnerability before they cause harm. The evidence base of our claim: these patterns have been identified through decades of outbreak investigations, facilities assessments, and root cause analysis across the following sectors. They have been identified in ready to eat meat facilities that had multiple outbreaks across different countries. The same patterns have been identified across fresh produce uh, operations sector, including the Jensen Farms cantaloupe that we said earlier and various E. coli outbreaks. The same patterns have been identified in daily processors. Sectors include Bluebell, Fonterra, and various Listeria events, and the same patterns were also identified in peanut and nut processing sector, including the PCA, the Sunland Inc., and also virus Salmonella incidences. The same pattern were identified in supply chains sectors, which had multiple salmonella incidents across global supply chains, and also the same patterns identified in seafood operations that include the Vibrio and histamines issues in various regions, and also the same patterns identified in bakery and confectionery, and that includes Cadbury, Salmonella, and various allergen incidences. Now, this is specific hazard. There is specific hazard for each or for every sector or every company or organization differ, but the failure patterns remain constant, and those are the patterns. The first pattern, failure is always slow at first. We will study this in details, and we will also show you how the standards and your design, system design, can apply the control measure. We will also show you how dangerous this is. Secondly, the second pattern is that controls break at interfaces. The third pattern, which has been identified in all these sectors, is that problems move forward instead of being stopped. The fourth pattern is that evidence becomes symbolic. And the fifth pattern is that pressure always wins without design. Don't worry, if you don't understand, we will explain and we will study them. And we will prove those are the reasons. Understanding these patterns allows you to recognize failure conditions before they cause harm. More importantly, it allows you to design systems that interrupt these patterns systematically. First, let's have an overview in the first pattern, which is failure is always slow at first. This is perhaps the most misunderstood aspect of the food safety failure. Catastrophic failures rarely begin as crisis. They begin as comfort. The mechanism of how failure is always slow at first, failure accumulates slowly through a process called normalization of evidence. Sorry, no, normalization of deviance. When deviation happens small, slowly, and people adapt it and it become normal, that process is called normalization of deviance. Okay? And I will explain more now with real world example. And also will give you a case that happened. A small deviation from standards occur without immediate consequences. So this lack of consequences create comfort, and comfort leads to acceptance, and acceptance becomes the new normal. The new normal creates a space for larger deviation. Now, why these patterns is universal? Human perceptions adapt to gradual change, right? So we notice sudden shift but become blind to slow drift. A temperature probe, for example, reading zero point 0.5 Celsius low today feels identical to yesterday, but 6 months of zero point 0.5 Celsius drift mean your pasteurization process is now operating 3 Celsius degrees Celsius below critical limits, but it still feels normal. That's the process of uh, normalization of deviation. Now, let's take a look at the case of the Bluebell ice cream evidence in 2015. Bluebell Creameries, a beloved Texas brand operating for over 100 years, experienced a listeria outbreak that killed 3 people and sickened 10 others. The post outbreak investigations revealed the following. First, in 2013, environmental monitoring detected listeria in non-product contact area. They're swapping that routine. They detected that in 2013. And then in early 2014, Listeria was found closer to production area. And they considered, oh, this is manageable, it's not in the product. Well, in the mid 2014, positive environmental sample increasing in frequency. So the more swab this they do, the more they found positive results. Again, they ignored that. And then in late 2014, Listeria detected in finished product. But that they say that's a separate thing. It's irregular, it's sporadic, enough to seem like isolated incident. Well, then it comes to 2015, outbreak declared. Entire production was held and company nearly bankrupted, right? Now, each positive test felt like an isolated incident in the case of the normalization of deviation. The patterns of increasing contamination was invisible to those experiencing it daily, like the staff, right? No single day triggered alarm, yet the cumulative drift was catastrophic, as you can see. So, how does the normalization of deviation happen? It happened in four stages. Let's explore them. First stage is a small deviation. So, something slightly outside normal parameters occurs. It's minor, it's manageable, and doesn't cause immediate problem. So, people ignore it. Then, we move to stage two, which is normalization. The deviation becomes routine, people adapt to the new condition, and they say things like, oh, it's always been like this. And that becomes the explanation. Well, from this normalization, we move to stage three, which is confidence is built around this normalization. So, since nothing bad has happened, the confidence increases. The deviation is now seen as acceptable, not it seemed like acceptable and normal. Nobody care anymore. Well, after confidence is built, like from a small deviation to normalization of the situation, now the confidence is built around it. That's when we move to stage four, which is crisis erupts. The condition align in a way that turns the normalized deviation into catastrophic failure. That's the process. So failure rarely arrives as a crisis. It arrives as a comfort. This pattern directly connects to mutual one concept of historical confidence, right? If you watch our mutual one, we address there the historical confidence, which is the dangerous comfort that comes from the absence of negative consequences. Now let's explore this real world example how comforts become catastrophic. Consider this pattern is in a modern food processing facilities, a composite based on actual outbreak investigation. Let's explore together for explanation. I will use this real world example to explain to you what we just talked about, the normalization of deviation. So let's start. In the first months, let's assume a temperature probe in the pasteurization system begins reading zero point 0.5 degrees Celsius lower than the actual temperature due to gradual sensor drift. The product still meets the specifications, no customer complaints, so the product continue. That's in the first month. Then we move to the second month, to the third month. The drift now reaches 1.2 degrees Celsius. Monitoring record shows consistent readings just above critical limits. The quality team notes the trend but doesn't trigger the alarm or for actions. Readings are still in spec. So maintenance is scheduled for after 3 months, and people say we can manage now until 3 months come and we will manage it. Well, Then in fifth month, now the drift reaches 2.5 degrees Celsius. Actual pasteurization temperature now occasionally drops below critical limits, but the probe doesn't detect it. Microbiological testing shows slightly elevated counts and attributed to raw material variation and production continue. Well, in month 7, drift reached to 2.8 degrees Celsius. Product is now regularly under pasteurized. Environmental monitoring detects pathogens present. Root cause investigation begin. But product from the previous 3 months is already in distribution. Well, the critical insight here, at no point did anyone make a conscious decision to produce unsafe food. Each felt normal, each decision seems reasonable in isolation, yet cumulative effects was systematic under processing of product for months. So why this happened? First, daily monitoring showed acceptable reading. Thus the probe was wrong, but nobody knew. Secondly, each month's data looks similar to the previous month's. Thus the gradual drift is invisible there. Then, thirdly, no immediate consequences reinforces the comfort. So contaminations takes time to manifest. Then fourthly, production pressure discourage overreacting to minor trends. Sometimes when somebody want to stop in some organization, they will tell you just overreact. You're just, you're not a team player, such things. So nobody want to overreact to minor trends because stopping production is expensive. And we will explain what do we mean by all this later. Now, this is pattern one in play. Failure is always slow at first. So by the time it becomes obvious, it's already catastrophic. This temperature probe failure wasn't the cause. The gradual acceptance of deviation was the cause. Systems must be designed to prevent normalization of deviation. That's the first pattern, right? Not just detect the problem. And we will design it together. Let's explore the second pattern, which is control breaks at interface. Most food safety controls are designed for processes, but failure lives between them, the interfaces, the handover between different people, systems, departments, or organizations. Those are where control most often break down. Let's explore, for example, between supplier and receiver. That's a critical information failed to transfer with products. That's an interface. Another interface we have between shift A and shift B. Incomplete communication of processes status and issues. That's another risk there, an interface. Thirdly, we have between Department A and Department B different priorities and understanding of requirements. That's a gap, that's an interface there. Thirdly, we have company A and company B. Between them, that's the handover is the interface. So ownership gaps and responsibilities confusion is the risk. And then we have between country A and country B, different regulatory systems and cultural expectations. Proper communication there. The gap in between the interface is where the risk is. That's where the control breaks. Now, most food safety controls are designed for processes, but failure lies between these processes in the interfaces. This is why modern food system requires explicit interface management. And if you see in our previous module also we have designed, even in our quality safety system, We have designed the interface management, not just the process control. Let me demonstrate that with real-world example when the interface breaks control. Consider these common interface failure patterns based on actual outbreak investigation in seafood supply chain. The setup is the following. The frozen seafood processor received raw materials from fishing vessel. The processor has an excellent HACCP control for their facility, and the fishing vessels follows good handling processing. Both parties are certified. Both have documented process, right? Documented procedures. So everything here seems perfect. Well, then the interface gap here, the fishing vessel's time temperature records shows proper handling. The processor's receiving records shows proper temperature, frozen temperature also. But nobody where tracks what happened during the 4-hour temperature transfers between vessel and the and processor cold storage, right? So everyone have temperature records are perfect, but the 4 hour during the handover, which I will explain now, nobody talk about that. So what actually happened in that 4 hours? First, the vessel crew begins offloading at 6 a.m. when their shift ends. So they finish offloading at 6 a.m. Okay. Then the product sits on the dock during transfer, which is outside the ambient temperature at 28 Celsius degrees Celsius. Thirdly, the processor receiving team, they arrived at 8 a.m. for their shift. That's after 2 hours, right? And product is moved to cold storage and temperature are recorded are acceptable. And they didn't arrive at 8 and immediately. It could have taken there more time. Both parties have documentation showing compliance. The hidden reality here, product experienced more than 2 hours of temperature abuse in the interface between two control processes at the flooding and loading dock, right? Where the vessel finished at 6 a.m. and the second party came around 8. Neither party's monitoring system captured these 2 hours in between. Neither party felt responsible for it. The interface became a blind spot where controls disappeared. Now you can see. Now the outbreak, when it happened 6 weeks later, histamine poisoning cases emerge. Investigation traces back to these interface failure. The temperature abuse during the transfer allowed histamine formation in susceptible species. Both the vessel and processor had perfect documentation, but the interface had no control. Why this pattern is universal? It happened everywhere around the world. Okay, this gap. You can investigate it in Africa, you can investigate it in Middle East, in China, in Brazil, in USA, in Europe, everywhere you go, you will find such interface. So why does it happen universally? Modern food systems involve multiple handovers. The first handover from supplier to receiver, the information fails there to transfer with products. And then you have between shift A and shift B, there is an incomplete communication of process status there. That also caused this pattern to happen. Okay? The interface failure here to happen. Then between department to department, that interface, the different priorities, different understanding also caused this interface to happen. Then company A and company B, the ownership there, the gaps, the responsibility confusion in between also allow this interface failure to happen. Then you have between country A and country B, They have different regulatory systems. They have different cultures, different expectations, and that allow this interface failure to happen. Now, each interface is an opportunity for control to break down, even when both sides of the interfaces have a strong controls, like we demonstrated above there. So each party could have strong control, but if the interface is ignored, that's the loss of control there. Interface failure are not about poor performance, they are about system design that doesn't count for handovers. Every interface requires explicit control design, and we will demonstrate that. Now let's have an overview again for our for the third pattern, which is problems move forward instead of being stopped. Modern food systems, problems have a tendency to move downstream rather than being caught and resolved upstream. This happens because stopping problem is harder than passing them forward. All right. So when a problem happens, people will just pass it on and get rid of the responsibility. I will demonstrate now. The economic reality for that, stopping a problem means the following. Stopping a problem means you are holding a production because that will involve immediate cost. The investigation of root causes will consume time and resources. Implementation of corrections, that means you need to invest another cost, and then potentially discarding products. So if the products is not good, it needs to be disposed, and that's a direct cost. Those are the economic reality that don't stop the problems, right? So what happen if the problem is passed forward? The following happen. Instead of stopping and bearing all these causes, if they pass it forward, the following will happen. Production will continue. Production doesn't stop. The revenue is maintained. And then problems become someone else's responsibility. So they get rid of the responsibility there. Immediate costs are avoided. You don't need to invest in investigation or corrective actions or disposing the product or rework. And then consequences are delayed and diffused. Now, why this pattern persists everywhere around the world? In complex supply chains, the party who can most the party who can most easily detect problem is rarely the party who bears the greatest consequence of the problem. This creates a systematic incentive to pass problem forward, and I will explain now with example. Okay, the 2024 evidence. Let's look at that. Prepared food, pasta, noodles, and salad accounted for the highest number of recall globally in 2024. Do you know why? Because these products involve multiple processing steps and multiple suppliers. Each interface is an opportunity for problem to move forward rather than being stopped. The international evidence, the 2008 China, we explained that in our previous module also. The melamine scandal perfectly illustrates pattern 3 on a massive scale. Now let me explain, give you bullet point of what happened in China in 2008, the melamine scandal. What happened there? First, dairy farmers diluted milk with water to increase the volume. Then secondly, they added melamine to mask the reduced protein content in the milk. So they want to raise the protein up, they added water. Then the salt collection stations. So now they don't have any problem. They added the melamine, the protein is high, sold it to collections. They are free of the problem now. The problem moved forward. Okay, and this is one of the also problem move forward is a pattern. Then collection stations sold The processors, again, they move the problem forward. They get rid of the problem. Then the processors sold to manufacturers. Again, problem moved forward. And then manufacturers sold to consumers. Again, now the problem has reached the end user. Well, the result there 300 babies, 300,000 babies were victims. Okay? 300 babies, 300,000 babies. And you can read this in Wikipedia. It's available everywhere, publicly available information. And 54,000 hospitalization and 6 infant deaths. At each interface, economic incentive favored passing the problem forward rather than stopping it. Each party couldn't claim they received it that way or meet the specifications. These same patterns occurred in legitimate supply chain when stopping problem is harder than passing them forward. Now, let's see the mechanism of passing things forward, how it does it happen, or passing the problem forward. First, let's say supplier detects a marginal quality issues. They will ship it anyways because customer will handle it, they will say. Then the receiver will detect the issue. They will use the product anyway. They will say, we can blend it out, mix it with other product, and get the average and meet the specifications, and we are fine. Then the processor detected the issue, the blended issue. Then the processor will say, let's continue the production. We will catch it in the finished product testing. Then the distributor will detect the issue. They will ship it anyway, and they will say the retailer will manage a recall if needed. If not needed, we don't have any problem. Well, each decision seems rational in isolation, but collectively, they ensure problems reach the consumers. And the underlying implications for this happens first, detection occurs downstream. Problems are often identified by customers, consumers, or regulators rather than by the system that created them. Then the silence move upstream. The information about the problem often fail to travel back to the source where they could be prevented. Thirdly, risk get transferred. So instead of solving problems, they get passed on, they get passed to the next party in the chain who has less ability to address these problems. So when problems are allowed to move, systems teach failure how to travel. This pattern is essential for understanding traceability, for understanding governance and leadership challenge that we will cover in later modules. Let me demonstrate that with real-world example how problems learn to travel. Consider this pattern in a spice supply chain based on actual salmonella outbreak investigation actually. So the origin, a spice farm in Southeast Asia occasionally has moisture control issues during monsoon season. Proper drying requires expensive equipment and also extended processing time. That's a loss for them. So rather than invest in better controls and time, the farm learns to manage the problem differently. What does they do? They adapt to it. They do the following. First week, the moisture level is slightly elevated. They will ship it anyway, and they will say, buyer doesn't test every lot. And then in the third week, the buyer detects the elevated moisture. They will accept it, blend it, and then they will plan to re-dry at their facility. And in week 5, the buyer's re-drying process is overwhelming. It's too much. So they will blend the high moisture lot with the dry lots to meet the average specification, you know. And then In week 8, the blended products was shipped to food manufacturing, and the food manufacturer said this meets the specification on paper, but some particles remains under dried. Well, in the week 12, the manufacturer used the spice in ready-to-eat products, and they assume that the supplier certification means safety. The outbreak now has happened. 6 months later, salmonella cases emerged across multiple states. Investigation traces back to the original moisture control issues at the farm, but the problem traveled through 4 companies and 3 countries before it reached consumers. Why each party passed this forward is because of the following. First, the farm, they said, we disclosed the moisture issue in our COA and buyer accepted it. Well, the buyer would say, we implemented additional processing, product met its specifications. Then the manufacturer would say, we purchased from a certified supplier, we verified their documentation. Then the distributor would say, we maintain proper storage, product was within shelf life. So each party now had documentation, each party followed their procedure, yet the problem traveled uninterrupted from farm to consumer. You see that? Now this is a system issue. Not single party had both the ability to detect the problem and the incentive to stop it. Let's say the farm could detect but lack the incentive. They will lose sales. They don't have incentive to stop that. If they take time to do additional drying and buy equipment, the competitor would take the sales from them. So they don't have the incentive. So they pass it forward. If we come to the manufacturer had the incentive to avoid the outbreak but couldn't detect it. The problem was hidden in blended product. So you see, nobody had both. This is why modern food safety requires explicit control at interface, which we will do shortly, and we will teach you exactly how we will go through it step by step. Also, we'll show how we meet the requirement of the standards. We need to explicitly design control for the interface and not just within facilities. Now, let's explore the fourth pattern, which is evidence becomes symbolic. In complex systems, evidence of controls can become separated from actual control. Records exist, monitoring occurs, verification are documented, but the connection of the real safety is lost. How this happen? When systems become complex, we rely on evidence as a proxy for reality. We can directly observe safety, so we observe evidence of safety. And over time, producing the evidence becomes the goal, and the connections to actual safety fades. I will explain with a real world example, don't worry. Now, the mechanism of how this happened first, in initial stage, monitoring is implemented to verify the control. That's good. Then the transition stage happens. Secondly, monitoring become routine. It just to generate the records. Well, then they move to the third stage, which is symbolic stage. Records become the goal. Actual controls become secondary. Then in the fourth stage, which is failure, is where the records exist but no longer reflect reality. The 2024 evidence, labeling error, undeclared allergen. Label error include undeclared allergen and incorrect nutritional value, were the leading cause of FDA recall in 2024. You know why? Because labeling verifications become a documentation exercise rather than a safety verification. Let me demonstrate that with this incident from 2013 in Europe, and is available on this link on Wikipedia. You can read it. The horse meat scandal evidence in Europe. Pattern 4 was perfectly illustrated when horse meat was discovered in beef products across Europe through the following. First, suppliers provided documentation showing 100% beef. Then, manufacturers filled certificates of authenticity. Manufacturers filed the certificate of authenticity. Then, retailers verified that documentation was received. Then, everyone had paperwork showing compliance. All right? But nobody verified that the evidence reflected reality. DNA testing eventually revealed that some beef, so called beef products, contained up to 100% horse meat. The evidence existed and satisfied requirements, but it was completely disconnected from reality. The documentation had become symbolic, a ritual that satisfied audit but ensured nothing about actual product composition. The real world patterns are the following. Labels are verified by comparing new labels to previous labels, not to actual formulation. That's the usual, right? And then certification of analysis are filled without anyone reviewing the actual test results happen. And then supplier audits are scheduled and completed, but finding don't trigger actions. These are the steps, by the way, that make the evidence become symbolic. Thirdly, HACCP monitoring records are filled out, but nobody analyzed trend. Fourthly, corrective actions are documented, but effectiveness is never verified. Those are how evidence becomes symbolic in real world. Now, the critical insight here, the evidence exists, the documentation is complete, but the evidence no longer connects to reality. It has become symbolic, a ritual performed to satisfy requirements rather than ensure safety. So, why is this dangerous? Because symbolic evidence creates false confidence. Everyone believes the system is working. They will say, look, we'll have all the documentation, while actual control deteriorates. Now, those are the underlying implications. Monitoring without response. Data is collected and recorded, but no one acts on deviation or trend that indicates developing problems. And we will examine this as we go through and explain with real world example and step by step how to do this. Secondly, verification without challenge. Verification activities confirm that the processes happen, but not whether they achieve their intended safety outcomes. Thirdly, audit without learning. Audit activities focus on compliance, documentation, rather than effectiveness of control in preventing actual risks. Let me demonstrate now with a real world example when the evidence replaces reality. Consider this common pattern in supply chain management, and this has been observed across multiple outbreaks also. Investigation. The system design. Food manufacturer requires all suppliers to provide certification of analysis, COAs, with every shipment. This seems like a robust evidence-based control, right? But the manufacturer has documentation proving every ingredient was tested. Now, the reality is, over time, the COA systems become symbolic. And this is how it happened. In the first year, the, f- it was a functional control. There was a functional control through quality team review each COA against the specification. Then, out of spec results trigger investigation and rejection, and also supplier knows their results will be scrutinized, and then the system creates real accountability. Well, now in the second year, transitions to symbolic. First, volume increases, quality team is overwhelmed, then COA review become a tick box. COA is received, yes, that's it, accept. Thirdly, supplier learn that COA are now filled but not scrutinized. Well, some suppliers begin providing a standard COA rather than the actual test results. They know nobody's checking there, everybody's overwhelmed as they start doing those games. In the third year, the COA or the evidence become fully symbolic. How? Through the following. First, the COAs are automatically filled upon receipt. Secondly, nobody reviews actual test results anymore. Thirdly, some COAs are for different lots actually than what was shipped. Then some COAs are months old and have been reused also for multiple shipments, and that happened. And number four, some COAs shows failing results, so but nobody noticed. Now even the suppliers start when they have a failing results, they will just ship it anyway. They know nobody's checking there anyhow, because now it's fully symbolic. The outbreak now happened. A pathogen contamination occurs in raw material. The supplier's COA shows the contamination. The test result positive for salmonella, but nobody at the manufacturer reviewed it. The COA was was filed, the box was checked, and contaminated material entered production. Post-outbreak investigation revealed the following. Manufacturer said, we require COA for all ingredients. We have documentation. Well, the auditor said, did you review this COA? Manufacturer said, it was received and filed per our procedure. Then the auditor said, the COA shows salmonella positive. Did, it, did that trigger any action? And the manufacturer responded, we did we didn't see that. We just verify that we received the COA. Well, the lesson here, the evidence existed. The documentation was complete, but the evidence had become symbolic, a ritual disconnected from actual safety verification. The manufacturer had evidence of control without actual control. Evidence requirements must be designed to detect actual risk, not just satisfy the expectations. And the purpose of documentation is to enable control and not to replace it. And we will design it together as we progress. Now let's explore the fifth pattern, which is pressure always wins without design. The production pressure is inevitable in commercial food systems. This pressure doesn't cause failure directly. Weak design does cause the failure, actually. Systems must be designed to observe pressure, not ignore it. Now, the reality of commercial food production is the following. Every food business faces the following pressure. First, they face the pressure of customer demands for faster delivery. Then seasonal peak requires increased capacity. Then equipment breaks down during critical production periods. And also the pressure of a staff shortage during high volume times. And cost pressures require efficient improvement. And the other pressure is competitive pressure requiring faster innovation. This pressure is not a failure of management, it is the nature of commercial operations. So, why this pressure reveals design weakness? Well designed systems maintain control under pressure, but poor design systems collapse under pressure. And we will show as we progress how to design that. The pressure doesn't change, but the design determines the outcome. Now let's look at the 2024 pattern. Recall search, the recall search 93% for the foreign material contamination, including glass, plastic, metals in 2024. Why is that? Because foreign metals controls are often the first thing to fail under pressure. The reason are the following. Inspections are rushed or skipped. Equipment maintenance is deferred. Temporary repair are made instead of proper fixes. That means the maintenance sometimes they will use the break time, to put the tape and all these things just to keep the product going because the priority is the throughput, not the safety here. Some organizations, and then cleaning procedures also are shortened, especially under pressure, and then the staff work longer hours with reduced attention. Now, the design failure here, these systems were designed to assume control operating, uh, to assume normal operating conditions, but they had no capacity to absorb pressure. When pressure increased, controls disappeared. The critical distribution here, or the critical distinction here, in weak design, they will say follow the procedure and assume that, uh, which assume the ideal condition. Just follow the procedure. But the strong design, the procedure works even under pressure because it's designed for reality. And we will explain that shortly. Examples of pressure resistance design include automated controls that don't depend on human attention, redundant systems that maintain function when primary systems fail, physical barriers that prevent contamination regardless of procedures compliance, and mistake proofing that makes error impossible rather than unlikely. Now, strong systems assume pressure will occur and design accordingly. These are the time of pressure. First, you have time pressure. You have the deadline, customer demand, and production schedule that compresses decision making time and reduce through thoroughness of check. Then you have cost pressure, the financial constraints that encourage shortcuts, reduce redundancy, and defer maintenance or upgrade. And then you have volume pressure, high production demand that strain capacity and make systematic controls difficult to maintain. And then also you have complexity pressure, multiple companies force demands that force choices between conflicting requirements or priorities. So the pressure does not cause failure, but weak design does cause failure. This reframing protects credibility with operations and leaderships, especially the audience here, by acknowledging pressure as inevitable rather than problematic. So we know it exists. All we just need to do is to design correctly. Let me demonstrate with real world example how pressure reveals design weakness. First, consider this pattern during a weak production period, a composite based on actual outbreak investigation also. The situation. The bakery received an urgent order for 50% more product than usual capacity. So the order is profitable. Just let me put this spotlight on again. Uh, the order is profitable and from a key customer. So management accepted it, and this creates immediate pressure across all operations. Now, the cascade of design failure. First, in the first 1 to 4 hours, the pressure starts. Line speed increased 30% to meet volume targets, and metal detector sensitivity is reduced to decrease false rejection, so more products can pass through. And then the visual inspection time per unit is decreased from 3 seconds to 1 second. Fourthly, staff began working extended shifts. Now, that's in the first 4 hours. And then in the 5 to 8 hours, the second part of the first shift, the maintenance pressure starts by scheduled equipment cleaning is shortened from 45 minutes to 20 minutes. And then a mixture blade shows wear, but replacement would require another 2 hours downtime. So they don't want to do that. They continue with the production. And the decision was we will replace it after the order is completed. Then the temporary repair is made with non-food grade adhesive. What we said earlier, they made they use the brakes just to put temporary repair, but now also here they exaggerated of making non-food grade adhesive. And then in the second shift, from 9 to 12 hours, the quality pressure starts. By environmental monitoring is now deferred, and they say we will catch up tomorrow. And then allergen changeover procedures are rushed. And thirdly, cross-contamination controls are temporarily adjusted. And fourthly, documentation falls behind actual production. Now, in our 13 to 16 safety pressure, the following starts. The staff are fatigued from extended shifts. Attention to details has decreased at this point, and small deviations are going unnoticed. And now the good enough becomes the standard. The outbreak here, or the outcome, 3 weeks later, customer complaints emerge. Metal fragments in products uh, from the worn mixture blades, remember, is is found, and also undeclared allergen from rushed changeovers, and foreign materials contaminations from inadequate cleaning. Now, the root cause here, not the pressure itself. Pressure is inevitable, but the root cause was design weakness as following. Metal detections relied on manual sensitivity. Okay, so sensitivity adjustment that should be logged. And also, the equipment replacement decisions were made under production pressure. Should have been automated based on wear indicators. Thirdly, cleaning time should be shortened, have been shortened without immediate consequences. There should have been minimum time log also for the cleaning. And then the quality checks depend on human attention during fatigue. The check should have been also it automated here. And that's the design weakness. So the lesson here, every control that failed under pressure was designed assuming ideal conditions. A strong design, however, assumes pressure and build controls that maintain function regardless of operational stress. Now, the certification's reality, why certified systems still fail? Because all the examples that we demonstrated, most of them or all of them are certified. This section here must be handled respectfully and carefully also, while acknowledging an uncomfortable truth. Respectfully, certifications does not prevent failure patterns. The evidence for this claim, the Peanut Corporation of America facility that caused 9 deaths in 2009 had the following. Regularly inspected by state and federal authorities, it was operating under approved HACCP plans, and it was subjected to third-party audits, and also it was supplying major national brands. Now, yet catastrophic failure occurred. Internal documents later revealed that 12 positive salmonella tests that were ignored and products were was shipped before test results were received. This is not a unique to Peanut Corporation of America. So now let's see why certifications doesn't prevent failure patterns. Certifications verifies design, not performance. So if standards like FSSC 22000 or SQF and BRC, they verify that you have designed appropriate controls. They verify documentation and they verify the procedure and the system, but they cannot verify that these controls maintain effectiveness over time under operational pressure. Audits are a snapshot, not continuous monitoring. We have to acknowledge that because audits capture one moment in time and typically ideal conditions as following when the audit happened. Facility is prepared for audit, best practices are demonstrated, documentation is current and organized, and also staff are briefed and attentive. But failure patterns emerge between audits, during normal operations, and under pressure. That's the reality. Standards also address known hazard, not systematic patterns, because food safety standards are excellent at addressing a specific hazard, such as biological, chemical, and physical hazard. They are less effective at addressing systematic patterns like what we discussed earlier normalization, interface, failure, and symbolic evidence. Because first audits are periodic, certification audits occur annually or biannually, right? Systems drift between audits and failure patterns can develop in interval during the interval time, right? Now, also, audits are sampled because auditors examine selected records and processes. Failure patterns may exist in unexamined area or merge between samples. Thirdly, audits focus on compliance. Certifications confirms that required elements exist, not that they effectively prevent the five failure patterns that we have discussed. So certifications at this point confirm system presence, not systems strengths. The respectful truth in regard to that is certification is necessary and valuable. It provides a foundation for food safety management, but it is not sufficient to prevent failure patterns. Certified facilities can and do experience catastrophic failure, not because certification is worthless, but because failure patterns operate at different level than certification addresses. How failure patterns emerge in certified system? Let's explore that. Certifications provide a foundation for food safety system, but failure patterns can still emerge. Understanding how these happen is critical for preventing it. Now, let's explore that. First, pattern is slow failure, right? So the system gradually changes after certification. Staff turnover, operational change, and process modifications occur or happen without systematic impact assessment. Now, audit finds minor nonconformance and corrective action is documented. Then the next audit defines similar issues and another corrective action is documented. Patterns of recurring issues develop, but each individual audit shows corrective action is taken. This is now normalization is happening between audits and gradual drift becomes invisible. So by the time the pattern is obvious, significant deterioration has happened. That's first. The second pattern, which is interface failure. Certification audits focus on individual sites. Failure patterns that happen at interface between certified site may not be examined. And this is how supplier is certified to FSSC 22000 and manufacturers trust the certification. Manufacturer is certified in SQF and distributor trusts the certification. Then each party has strong internal controls, but interface between them has gaps. And information doesn't transfer with products, so critical handling requirements are lost. Then both parties maintain certification, but the interface remain uncontrolled. Third pattern, which is problems move forward. Suppliers first detect the issue, then documents it in COA as required by standard. Manufacturer receives COA, files it as required by standard. Both parties have documentation and both maintain compliance. But the problems move forward and nobody stopped it. The standards requires documentation but don't require stopping the problem. Now, the third pattern, which is symbolic evidence, over time, maintaining certifications become about satisfying auditor expectations rather than providing actual risk. First, auditors verifies that monitoring occurs, checks records, confirm frequency. Then auditor verifies that corrective actions are documented, review forms, and then auditors verifies that procedures exist, confirm they are accessible. But auditor cannot verify that monitoring is meaningful or that corrective actions are effective. Evidence exists and satisfies the auditor, but it may be disconnected from reality. Now, the fifth pattern, which is pressure wins. Certified systems may not be tested for their ability to maintain control under the operational pressure they will actually face. Systems is designed and audited under normal conditions and it pass certification. Then operational pressure increases. System is stressed beyond now the capacity. Then controls begin to fail, but next audit is months away. By the time the audit occurs, either failure has happened or pressure has subsided. Audit sees systems under normal conditions and it cannot detect pressure related vulnerability. The critical insight here, these patterns don't indicate um, these patterns don't indicate that certification is inefficient. They indicate that certification is addresses one layer of food safety, system design and documentation, while failure patterns operate at another layer, system performance under real world conditions over time. Both layers here matter, the layer of system design and documentation and the layer of performance under real world conditions, but both require attention. Now let's explore the danger of normalization. Normalization deserves special attention here in our module today because it underlines all five failure patterns. It is the process by which dangerous conditions become comfortable through familiarity and lack of immediate consequences. First, let's see the psychological mechanism of the normalization. Human perception is designed to detect change, not absolute state. We notice when things get suddenly worse. We don't notice when things get gradually worse. This is a feature of human cognition, right? Not a flaw, but it creates systematic vulnerability in safety critical systems. How normalizations enables each patterns? Let's explore that. The first patterns, which is a slow failure, the normalization is the mechanism here because each small deviation feels normal because it is only slightly different from yesterday, but cumulative drift become invisible. Then the normalization enables also the second patterns, which is interface failure. Interfaces normalize because they are invisible. We see our own processes clearly. We see our partner's processes clearly, but the gap between them normalizes because we never directly observe it. Normalization also enables the third pattern, which is problem moving forward. Passing problem forward normalizes because it works. No immediate consequences means the behavior feels safe, but over time it becomes a standard practice. The fourth pattern also is enabled by normalization. The fourth pattern, which is symbolic evidence. Evidence becomes symbolic through normalization. We stop checking whether evidence reflects reality because it always has in the past. The disconnect normalizes gradually. Then we have the fifth pattern, which is pressure wins. Now, operating under pressure normalizes. The first time we skip a step under pressure, it feels wrong. The 10th time, it feels normal. But the 100th time, it's just how we work during busy period. Now, how does that circle play out? Let's explore together. Firstly, there is alert response. Initial reaction to unusual conditions is heightened at this point, and attention and concerns are heightened also. And then we move to adaptation. People and systems adapt to work around the unusual condition. Thirdly, comes normalization. The unusual becomes the routine. Concerns decreases as people become comfortable with adapted state. Then fourthly, invisibility happen. The original deviation is no longer noticed. It has become the new normal, and the circle continues. Now, the most dangerous failure are the ones that stop feeling dangerous, generally in life. The PIP breast implant scandal evidence in France in 2010. Okay? While this is not a food case, this medical device case perfectly illustrates the normalization in manufacturing. Polyimplant protease or PIP, a French company, gradually substituted approved medical grade silicone with industrial grade silicon over several years. And this is how it happened. First, in the year 2000 to year 2001, a small percentage of industrial silicon was mixed in to and to save the cost, and that went unnoticed. Then in 2022, between 2022 and 2020, between 2002 and 2004, ratio of that industrial silicon increased gradually, and there was no immediate problems detected, no consequences. Then in the year 2005 to year 2007, majority of implant using industrial silicon practice fully normalized. They started small, they increase, no consequences. Now they move to majority to adding industrial silicon into their practice. Then in between the year 2008 and 2010, increased rupture rate notice but attributed to other factors. They say it's not our problem, right? Then in 2010, the scandal was exposed. More than 400,000 women affected globally. The company founder was imprisoned. So each batch they produced felt normal because it was only slightly different from the previous batch. Workers knew it was wrong initially, but over years, it becomes just how we do things here. Well, now let's explore the Fonterra also. And this you can find this in the Wikipedia. The Fonterra whey protein case in New Zealand 2013. Fonterra, the world's largest dairy exporter, experienced a botulism contamination scare in 2013. First, what happened? Dirty pipe work in one processing line gradually accumulated residue. Secondly, cleaning procedures were progressively shortened due to production pressure. Thirdly, each shortened cleaning cycle seems acceptable because the product was still past the test, was still within the specification. Then, over 18 months, the normal cleaning time, what they call normal now, decreased from 45 minutes to 15 minutes. Now, contamination occurred, triggering global recall of 38 tons of whey protein. The cost of that incident is 19 million NZD in direct cost. That's immeasurable brand damage there. The staff didn't consciously decide to do uh, inadequate cleaning. The standard gradually eroded through normalization. So why this matter? You cannot prevent normalization through willpower or attention. It is a fundamental feature of human perception. You can only prevent it through system design. And through system design, you do the following. Trend analysis that detect gradual drift. And we will design it together throughout this module. That's first thing you do, trend analysis, and then absolute standards that don't adjust to current conditions, and then external perspectives that are normalized to your environment, and then automated alert then don't adapt to gradual change. If you implement these four steps, which we will design together, you will prevent the normalization. Normalization is the enemy of safety. It must be designed out, not trained out. Real world example of how normalizations makes danger invisible. Consider these normalization patterns in a cold storage facility based on actual outbreak also. Now let's see the investigation. First week, the initial deviation. One of four refrigeration units begins cycling more frequently than normal. Maintenance is scheduled but not urgent since the other three units are functioning properly. The temperature monitoring shows all zones within a specification, so everything feels normal. Now, in the fourth week, the adaptation begins. The problematic unit now cycles constantly. Maintenance is scheduled due to production priorities. Temperature monitoring still shows compliance, though readings are trending toward the upper limit. The staff noted the unit is working hard, but product is still cold, and this becomes the new normal again. In week 8, compensations becomes the standard. The unit can no longer maintain temperature during peak loading period. So the staff adapt to that and they did the following. First, they start loading less products in that zone. Secondly, they start rotating products to other zones when possible. Third, they start checking temperature more frequently. Fourth, they start accepting readings at the upper specification limits. Now, these adaptations work. Products stay within a specification. The workload become a standard operating procedure. This also feels normal. Now, in week 12, the system degradation accelerates. In week 12, a second unit begins showing similar symptoms. Now, two or four units are compromised. The staff have normalized the workaround, moving things from here and there and not keeping a lot of product near the dysfunctional unit. It become their normal. So now they know how to work around it. And what they do, they reduce the loading. Reduce loading is they will just say this is just how we manage that zone. And then the frequency temperature checks now are being extra careful. They say. Thirdly, upper limit readings now are still within the spec. It doesn't trigger any alarm anymore. And fourthly, the situation feels under control. Well, in week 16, the catastrophic failure. During a heat wave, the two compromised units fail completely. The remaining two units cannot handle the full load. Temperature excursions occur across multiple zones, and product is compromised. Now, during the post-incident investigations, they found the following. First, the management said, "Why didn't anyone report this was getting worse?" And then the staff say, "We did report it, and maintenance was scheduled." The management will respond, "Why didn't you escalate when it wasn't fixed?" The staff will say, "We were managing it. Temperature was still within the specs." The manager and final will respond, "But two units were failing." The staff will say, "It happened gradually. Each week was only slightly worse than the latest." Now, this is the normalization process. In the first week, one unit is acting up. They notice, report it, nothing happened. The fourth week, the unit always act up. They start saying that normalization, that unit is just acting up. In the eighth week, they start saying, we know how to manage it. They adapted to that. In the 12th week, they start saying, this is just how we operate. They fully normalized at this point. In the week 16, the management start asking, how did this happen? Now that's the catastrophic failure. The critical insight here, nobody made a conscious decision to accept dangerous conditions. Each week felt only marginally different from the previous week. The cumulative deterioration was invisible to people experiencing it daily. Now, this is why external audits and trend analysis and absolute standards are essential. You cannot rely on daily operators to detect normalization. They are the one being normalized. And we will explore that shortly, how to design that. Now, the blame problem. Why blame makes system weak? Actually, especially in cultures where blame is prevailing. Understanding why blame is counterproductive is essential for building effective food safety system. This is not about being nice. It's about understanding how system actually work instead of just blaming, right? So let's explore that together. The blame instinct, when failure happen, the instinct to blame is powerful and it plays out like this. The instinct provides a simple explanation and you will say someone was careless, someone was lazy, or someone was incompetent. The blame instinct also will offer simple solution. Just punish that person or replace that person and you are done and you are safe. Also, the blame instinct protects the system. They will say if something happened, especially when major incident happen, people will say the problem was the person, not the design. And they get out with that. They get away with that. They keep their job, they fire that innocent person, and everybody is just, will lay back and wait for the next incident. And also the blame satisfies our need for accountability. Those are the blame instincts. But this instinct is systematically wrong about how modern food safety failure happen. First, why blame is wrong? Let me explain. Blame misidentifies the problem. That's why blame is wrong in the first place. And in case of the ginseng farms, cantaloupe, you remember in the first, in that outbreak which killed 13 people, who should be blamed there? The worker who cleaned the equipment following their training, or the supervisors who approved the cleaning procedures, or the managers who purchased equipment not designed for cantaloupe, or the owner who set production targets, or auditor who certified the facility. Who should get the blame there? Everyone was doing their job as they understood it. The failure was systematic, not individual. The equipment design was wrong for the product, creating conditions where proper cleaning was nearly impossible. Also, blame prevents learning because uh, when blame is the response to failure, people learn to do the following. People learn to hide problems rather than reporting them because they will be blamed, right? Also, people learn to document carefully rather than act concisely, uh, decisively. they become selective. Because if you document something that is not acceptable, you will be blamed for it also. And then people start following procedures exactly rather than thinking critically. Sometimes the solution needs other immediate interventions. But if they do so, they will get blamed. So they just follow the procedure and stay safe. Then when blame also it prevent learning because people start avoiding responsibility rather than taking ownership. Now, this makes system weaker, not stronger, evidently as you can see. Thirdly, blame ignores system design. If a single person's error can cause catastrophic failure, the problem is a system design, not the person. Strong systems are designed so that they can do the following. First, individual errors are caught before causing harm. That's the strong design. Secondly, critical controls don't depend on perfect human performance. Thirdly, mistakes trigger learning, not just punishment. And fourthly, reporting problems is rewarded, not punished. That's the strong design. The evidence from high reliability industries who have strong design. For example, in the industry of aviation or the nuclear power industry and the healthcare industry, they have learned that blame-free reporting system catches more problems earlier through the following. The pilot reports error without fear of punishment, right? There, the near misses are analyzed and prevented. There are actions there, and they are rewarded for reporting. Secondly, in nuclear industry, nuclear operators reports concerns without career risk. Small issues are fixed before becoming large. Thirdly, in healthcare industry, healthcare workers report mistakes openly and systematic improvement are made. In food safety, we must learn the same lessons and follow those industries. The underlying blame issues, blame hides risk. When people fear blame, they hide problems, report selectively, and avoid raising concerns that might reflect poorly on their performance. And also, fear kills early reporting. Because early detection of problems requires people to report concerns before they become crises. Fear of blame delay those crucial early warnings. Thirdly, silence increases harm. Problems that are hidden or delayed in reporting have more time to develop and spread through the system. Blame solves the emotional need for an answer, not the system need for control. This prepares, and this understanding will prepare us for later modules on cultures, leadership, and governance by establishing that effective systems require psychological safety, not punishment. Now, let's explore how blame culture enables uh, failure patterns. Blame culture doesn't just fail to prevent failure patterns, it actively enables them. Understanding this mechanism is critical for building effective food safety systems. The first pattern is slow failure. How blame accelerates normalization. The mechanism of how blame accelerates the normalization are the following. First, reporting a problem might be seen as creating the problem. Secondly, raising concerns might be interpreted as incompetent. They will say things like, why didn't you handle it? Thirdly, identifying issues might result in being assigned to fix them. You will be told something like, punishment by work, like go fix it, it's your problem. So that's a punishment by workload. Fourth, speaking up might damage relationship with colleagues who are managing the situation. The result here, how the results of how this blame culture now accelerating the normalization is through the following. First, warning signs go unreported. Secondly, normalizations accelerates. Nobody question deteriorating conditions. Thirdly, problems grow until they are undeniable. Fourthly, by then, catastrophic failure is inevitable. Now, let's demonstrate that through real-world example. In 2011 Listeria outbreak linked to Jensen Farms, Cantaloupe, USA, which killed 33 people, the deadliest foodborne outbreak in the modern US history. Workers likely noticed deteriorating conditions in the packing facility. But in a blame culture, reporting these conditions means admitting your area has problem, potentially being blamed for not preventing them. So that's creating work for yourself and others also, and risking relationship with supervisors and colleagues. Post-outbreak investigation revealed that employees actually had concerns about equipment cleaning, and also they had concern about water quality. But these concerns were not escalated because the culture didn't support the speak up, and they would have been punished for that. The second pattern, the interface failure, how blame creates information gap here. Let's explore together. The mechanism of how blame creates information gap is through the following. First, admitting you received a problem means you might be blamed for accepting it. Secondly, reporting that you pass problem forward means admitting you didn't stop it. Thirdly, acknowledging interface gaps means admitting your controls are not perfect. And finally, raising interface issues might be seen as blaming the other party. The results of such a mechanism are the following. Critical information doesn't transfer anymore. Problems at interface will go unaddressed, and both parties protect themselves through documentation rather than communication anymore. And interface gaps widen until catastrophic failure happens. Let's demonstrate that again through a real world example. Suppliers ships marginal quality material. Okay. Receiver noticed but accepted it because rejection means production delay and blame for disruption. Then suppliers learns that marginal quality is acceptable. So quality deteriorates further and further from the supplier. And eventually, contaminated material causes outbreak. Now, both parties have documentation protecting themselves, but neither communicated the problem. Now, in let's move to pattern three. Is problem move forward? How blame ensures forward movement. The mechanism of how blame ensures forward movements is through the following. First, stopping a problem means taking responsibility for the disruption. Secondly, passing problem forward diffuses responsibility, right? That's what happened. Thirdly, if the problem causes issues downstream, you can claim it met its specification when I released it. Well, fourthly, documentation protects you from blame better than stopping the problem inside mechanism. So you just rely on documentation and you don't stop the problem. As a result, the following will happen. First, a stopping problem is punished, blame for disruption. You are being blamed. Why did you stop the work? Now we are not meeting the target. Okay. Secondly, passing problems forward is now rewarded. No immediate consequences. Because if you stop it, you will be punished. If you pass it, you are relieved. Thirdly, problems systematically move toward consumers. And fourthly, when outbreak happen, everyone has documentation showing that they followed the procedure. Let me demonstrate that with a real world example. Production detects marginal product quality. Okay. The options are the following that the production have. First, stop the production. If they do so, immediate blame for missing targets, disruption schedule, losing revenue, and blah 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 will happen. All that will happen if they stop the production. The second option the production have when they detected the marginal product quality is to pass it forward. If they pass it forward, no immediate consequences and problems become QA's responsibility. So they pass it forward. Now, QA now detects the issues and have two options in this cultural type of the organization. The first option to reject the product. If the QA rejects the product, they will be blamed for the waste, they will be blamed for customer delivery, and they will be blamed for losing revenue. The second option QA has is to pass it forward. So if they pass it, there is no immediate consequences and problem become customer's responsibility. So they did pass it forward. Now, the blame culture ensures problem move forward at every decision, sadly. Okay? The fourth pattern, which is evidence becomes symbolic, how blames creates documentation theater. The mechanism of how the blames creates the documentation theater happens through the following 4 points. First, documentation protect you from blame. If you did proper documentation, you can just say, I followed the procedure. Done there. Secondly, documentation is easier to produce than actual control. Thirdly, complete documentation satisfies auditors and supervisors. And fourthly, if failure happened, documentation proves it wasn't my fault. Well, in such mechanism, the following are the results. First, efforts shift from ensuring control to documenting control. Secondly, evidence become disconnected from the reality. Thirdly, everyone has perfect documentation while actual controls deteriorates. And finally, when failure happens, investigation finds complete records but no actual control. Let me demonstrate that again with the real world example. Monitoring records are completed daily, showing perfect compliance, but nobody reviews them for trends. Nobody acts on concerning patterns, and nobody verifies they reflect reality. Why? Because of the following. First, completing records protects you from blame. Secondly, analyzing records might reveal problems and responsibility also to fix them. They will tell you, fix it is your problem. Thirdly, questioning records might be seen as questioning colleagues. And fourthly, perfect documentation satisfies auditors. Now, so records exist, audits pass, and actual controls deteriorates until catastrophic failure happen. Fifth pattern, pressure wins. How blames make pressure irreversible or irresistible. Sorry. The mechanism of how blame makes pressure irresistible is through the following. First, refusing to cut corners under pressure means blame for not being a team player. You are not a team player. Let's cut the corners in such culture. Secondly, insisting on full procedures mean blame for you are slowing things down. You will hear some things like that. Thirdly, stopping production under pressure means blame for, oh, you are just overreacting, man. This is a minor issue. Let the production continue. Fourthly, speaking up about pressure related risk means blame for making excuses. Okay? As a result of this mechanism, the following will happen. Pressure systematically override controls. People who resist pressure are punished. People who accumulate pressure are rewarded. And system design weaknesses are never addressed because acknowledging them means blame. And catastrophic failure during pressure periods become inevitable. To demonstrate that with a real world example, during peak season, production pressure increases. Supervisors suggest shortening cleaning time to maintain throughput. Now there are two options here. The first option, to refuse, that means blame for not being flexible, not understanding business need, and not being team player, all this type of talk, right? The second option here is to comply. If you comply, no immediate consequences, problems become invisible until outbreak. Now, the blame culture ensures pressure wins every time, as you can see. The systematic effects here, blame culture doesn't just enable individuals' failure patterns, it creates a system where the following happen. Problems are hidden, not reported. Information is withheld, not shared. Issues are passed forward, not stopped. Documentation replaces reality, and pressure overrides control. This is why blame culture is the enemy of food safety. The alternative, learning culture, which is learning culture, better one. Okay. So you have one evil twin, the blaming culture, and the good twin is learning culture. Now let's explore together. In a learning culture, you will find the following. Reporting problem is rewarded, and you will hear things, you are helping prevent failure in a real sense, genuinely. Secondly, communicating issues is expected in learning culture because transparency there is valued. Thirdly, stopping problem is supported in learning culture because you are protecting the organization. And evidence is verified in learning culture because we want to know reality, not just documentation. You will hear that. Then, fourthly, resisting pressure is respected in learning culture because you are maintaining the standards. That is the culture. As a result of such beautiful culture, the following will happen. Warning signs are detected early. Interface gaps are identified and closed. Problems are stopped upstream. Evidence remains connected to reality. Systems are designed to observe pressure. The evidence from high reliability industries are the following. In aviation industry, in nuclear power industry, and in healthcare industry, they have learned the following lessons. First, in aviations, they have learned pilot reports error without fear of punishment. Near misses are analyzed and prevented. Reporting is mandatory and protected. The results there, safest form of transportation. In nuclear power, they learned the following. Operators report concerns without career risk. Small issues are fixed before becoming large. Stop the work authority is protected and respected. The results there, decades without major incidents in modern plants. In healthcare industry, they learned the following. Medical errors are reported openly. Systematic improvements are made. Blame-free reporting systems catch problems early. The results there, significant reduction in preventable harm. Food safety must learn the same lessons from such industries. Let's go back to the boar's head outbreak occurred in a facility that has the following. On-site federal inspectors, documented HACCP plan, regulatory monitoring and verification, and certified systems. Yet 10 people died. That's in our industry. Why? Because the culture enables failure patterns through the following. Deteriorating conditions were normalized. That's part one. Information gaps between inspectors and managements. That's pattern two. Problems documented but not stopped. Pattern three. Evidence existed but was symbolic. That's pattern four. Production pressure override control. That's pattern five. A learning culture would have done the following. Detected deterioration through trend analysis, which we will learn together throughout this module. Communicated concerns openly. Stopped production when conditions deteriorated. Verified that evidence reflected reality. Designed systems to maintain control under pressure. The bottom line here is the following. Blame culture doesn't just fail to prevent failure patterns, it actively enables them. Every failure pattern is accelerated by blame and interrupted by learning. Let that sink in. Organizations must choose between these two options only. First option, blame culture. If you want to choose the blame culture as an individual, it will protect individuals, but it will enable failure patterns and you will experience catastrophic failures. Or the organization should choose learning culture where it protects the system, it interrupts failure patterns, and it prevents catastrophic failures. There is no middle ground. The culture you create determines whether the failure patterns are detected and interrupted or hidden and enabled. Now, your responsibility. If you are in a position to influence culture, do the following. Reward problems reporting, don't punish them. Celebrate prevented failures, not just perfect records. Support people who stop problems, don't blame them for disruption. Investigate systems, not individuals. Build psychological safety for speaking up. But if you are not in a position to change culture, do the following. Report problems anyway. It's your professional responsibility. Document your concerns. Protect yourself while protecting others. Thirdly, seek organizations with learning culture. They exist and they are safer. The choice between blame and learning is the choice between enabling and preventing failure patterns. Choose wisely. Now, let's explore the predictable failure. And failure is always predictable. This is the most important statement in this entire module, and it must be stated clearly and calmly. Most food safety failures were predictable. The warning signs existed. They were visible. They were often documented, but they were not acted upon. This is the truth. This is not hindsight bias. No, this is documented fact. There are evidence across multiple sectors. For example, in Peanut Corporation of America in 2009, congressional investigations revealed that management had documentation of 12 separate salmonella positive tests in their facility over 2 years before the outbreak that killed 9 people and sickened 714 people. The warning signs were documented, they were visible, but they were ignored. Production continued. In case of crypto or triple E. coli outbreak between 2015 and 2016, multiple outbreaks across different states revealed systematic gaps in supplier controls and food handling. Post-outbreak analysis showed the following. Supplier audit findings indicating risk. This is documented months before. And then employee reports of pressure to work while ill. This is also documented. And then the temperature control issues during peak period is documented also. And then multiple near miss incidents that weren't escalated. Now, if we reflect for the incident of Cadbury salmonella outbreak in UK 2006, internal documents shows that Cadbury detected salmonella in their factory in January 2006. They changed their testing protocols rather than stopping production. Outbreak occurred in June 2006, after which affecting over 100 people. The warning sign existed 5 months earlier. Let's reflect also for Jif peanut butter recalls in 2002. J.M. Smarker recalled Jif peanut butter after salmonella outbreak. Investigation reveals environmental monitoring had detected concerns trending months before the outbreak, but the pattern wasn't recognized as escalating risks. The universal patterns are the following. Warning signs existed months or years before catastrophic failure. Multiple people noticed and reported concerns. Documentation exists showing the deteriorating conditions. No single dramatic event triggered the outbreak. No, gradual accumulation of small failure led to catastrophe. Now, why predictable? Then why predictable failure still occur? You ask. Because of the following: warning signs are normalized because each individual warning sign seems minor, but taken together, they indicate systematic failure. But people experiencing them daily don't see the pattern; they see the individual issue being managed. Secondly, The predictable failures still occur because warning signs are documented but not analyzed. There are inspection reports, there are corrective action records, and monitoring data containing the warning signs, but nobody synthesizes this information to see the pattern. Each document is filled separately. The pattern remains invisible. The fourth reason, warning signs don't trigger escalation. Systems are designed to respond to specifications failure, not to patterns of deterioration. A single out of spec reading triggers action. Pattern of reading trending toward the limits doesn't trigger the action. And we will design that how to reverse that shortly. Fourth reason is warning signs compete with production pressure. Responding to warning signs requires stopping production, investigation of root causes, and implementing corrections. These expensive and disruptive, they say, and continuing production while managing. The issue is easier until it is catastrophic. The implication here, if failure are predictable, they are preventable, right? The question is not, could we have known? No, not anymore. The question is, why didn't we act on what we knew? This shifts the focus from blame of who failed to system design. Why did our system fail to act on available information? That is the question. Now, let's explore the practical implementation, detecting failure patterns warning sign. Since failure patterns are predictable, they can be systematically detected and interrupted. Here are specific actions, warning signs for each pattern. First pattern, warning signs, slow failure normalization. The trend analysis will reveal this. Monitoring data trending toward specification limits over time. If you conduct trend analysis, it will show you also increasing frequency of acceptable deviation. Trend analysis will show you growing number of corrective actions for similar issues. And trend analysis will show you longer time between equipment maintenance cycle. And also it will show you increasing use of temporary fixes or workload. The behavioral indicator here include phrases like, it's always been like that, or that's normal for us. And also there is decreased urgency in responding to minor issues. The other behavior indicator also is acceptance of conditions that would have alarmed staff previously. And the other indicator is new employees expressing concern about conditions that veterans consider normal. Pay attention to that. The documentation patterns include corrective actions that address symptoms but not the root causes, recurring non-conformances with similar root causes, increased time log between issue detection and resolution, and then growing backlog of minor maintenance items. The detection tools include statistical process control, charts showing drift, comparative analysis of current versus historical performance, external audits that identify issues and normalize internally, new employees feedback program, they see what veterans don't see actually. The second pattern is the warning sign, the interface failure. You have Information gap as the warning sign here, and that include critical products information not transferred with the shipment. That's warning sign. Different understanding of specifications between parties. That's another warning sign. Assumption about what other party know. That's another warning sign of the interface failure, and then lack of direct communication between operational and staff is another warning sign. The responsibility confusion also here include unclear ownership of interface activities, assumptions that someone else is handling it, and gap between where one party controls end and the others begin, and then define there is no defined process for interface handovers. The documentation disconnects here include supplier documentation doesn't match receiver expectation, time gap between products and documentations, and information loss during shift change or handover also, and different systems that don't communicate. The detection tools you need here include interface mapping exercise. We will do it together throughout this module also. Document any handover, communicate audits, verify information transfer, responsibility metrics, clarify ownership at interface, cross organizational process review. Pattern 3, the warning sign for problems moving forward. Economic indicators and warning signs for problem moving forward include the following. Cost of stopping problems exceed cost of passing them forward. Incentives that reward throughput over quality. Penalties for production delays but not for quality issues. And pressure to make it work rather than reject marginal products. Those are the economic indicators warning sign for problem moving forward. For behavior patterns that include phrases like the customer will handle it or we can plan it out. Also, the behavior patterns include increasing use of rework or reprocess, and then growing acceptance of marginal quality. And finally, for behavioral patterns, you have reluctance to reject supplier materials. The system gaps include no clear authority to stop the production, complex approval processes for rejection, lack of consequences for passing problems forward, reward systems that penalize stopping problems. So, and detection tools here include track rework and processing rate. That means increasing equals to problems moving forward and vice versa. And then monitor rejection rates at each stage. Decreasing means problems passing through and vice versa. Analyze customers' complaints for issues that should have been caught internally. And review decision-making authority for production stops. Now, in pattern for warning signs, evidence becoming symbolic. The documentation disconnects warning signs for evidence becoming symbolic include records completed but not reviewed, monitoring data collected but not analyzed, corrective actions documented but effectiveness not verified, audit findings closed without confirming resolution. The behaviors indicators here include focus on completing paperwork rather than verifying controls, resistance to changing documentation systems, treating audits as documentation reviews rather than system assessments, pride in having all the paperwork rather than documentation are demonstrating control. The system symptoms here include increasing volumes of documentation with increasing utility, records that don't trigger actions even when showing problems, verification activities that verify documentation but not the reality, compliance measured by paperwork completion, not by safety outcome. Detection tools here include random verification of records against reality, analysis of whether the documentations trigger appropriate actions, review of how monitoring data is actually used, and assessment of whether evidence comes to decision making. First, fifth pattern, warning signs for pressure winds. The design weaknesses for warning signs when the pressure winds include controls, controls that depend on human attention during stress, no redundancy when primary systems fail, pro- procedures that assume ideal conditions, critical steps that can be skipped under pressure. The operational indicator here include increasing frequency of exception to procedures, growing gap between documented and actual practical or practices, shortcut that becomes a standard during busy periods, deferred maintenance accumulating during peak season. The pressure points here include seasonal peaks that stress capacity, customer demands that exceed design capacity, equipment failure during critical procedures periods, staff shortage during high volume time. The detection tools here should include the following: stress testing of systems under simulated pressure, analysis of performance during peak versus normal periods, review of incidence rates during high pressure periods, assessment of which controls fail first under pressure. An implementation approach is as following. First, select the pattern most relevant to your operation. Secondly, implement detection tools for that pattern. Thirdly, establish threshold that trigger escalation. Fourthly, create response protocols when warning signs appear. Fifth, monitor effectiveness and adjust. And we will design further together also. The goal is not to detect every possible warning sign. The goal is to detect pattern early enough to interrupt them before they cause harm. Now, practical implementation standards clauses that address the failure patterns. Let's explore together. Modern food safety standards contain specific requirements designed to intra-failure patterns. Understanding these connections helps you implement standards more effectively. First, addressing pattern one, the slow failure normalization. If I'm speaking, if I'm speaking fast, you can slow down the setting on YouTube, and it will be clear, right? Or you can pause sometimes because these are critical information you need to observe. In FSSC 22000 and ISO 22000, addressing pattern 4, slow failure normalization, is addressed through clause 9.1.2, which is monitoring and measurement. It requires trend analysis, not just point in time compliance. It's also addressed through clause 9.3, management review, forces periodic external perspective on normalized conditions, and also is addressed through clause 10.2, which is non-conformity and corrective actions, requires root cause analysis to prevent normalization of recurring issues. And also, this first pattern is the normalization of flow issues. Sorry, falling asleep actually. Secondly, the SQF code is addressing this pattern one through the following: through the element 2.4.2, corrective actions and preventive actions, which is the element's title, and it requires analysis of the trend and patterns, and also it's addressed through element 2.5.3, which is internal audits, and it provides external perspective to detecting normalization. And then through elements 2.7.1, control of monitoring and measuring devices, which prevents drift measurement systems. Also, the first pattern is addressed through BRCGS or BRCG global standards through the following. In clause 3.5, which is internal audit, it's addressed through scheduled audit, interruption normalization. Clause 3.6, supplier approval, prevents normalization in supplier relationships. And clause 3.11, traceability, enables detection of the patterns over time. Then we have implementation tips here for the first pattern, preventing the normalization. Don't just comply with these clauses, use them as normalization detection tools. Trend analysis should specifically look for gradual drift, which we will do shortly. Management reviews should question the normal condition. Internal audits should compare current states to historical baseline, not just to procedures. Addressing pattern 2, the interface failure, we address it through FSSC 22000 and ISO 22000 through the following clause. Clause 7.1.6 address the interface failure through external communication, which requires explicit interface management, and also is addressed through clause 8.4.2, which is information for external providers, which specifies what must transfer at interface, and through clause 8.4.3, verification of externally provided processes, which requires interface verification. Also, the interface failure is addressed through SQF code through the following elements. Element 2.6.2 specifications defines what information must transfer. Elements 2.6.3 supplier approvals and monitoring manages supplier interface. And element 2.6.4 incoming materials controls receivers interface. It's also addressed the receiving the interface failure is addressed through BRC global standards following clauses. First, in clause 3.5.1, which is supplier approval, explicit interface management, and clause 3.5.4, supplier performance monitoring, which requires ongoing interface verification, and clause 5.4, product information and customer awareness, which requires customer interface control. The implementation tips here to prevent interface failure: map every interface in your operations, which we will do together shortly, between supplier and receiver, between receiver and between shift A and shift B, between department and department. Just map all the interfaces, and for each interface, identify what information must transfer, who owns the interface, and how is interface verified, and what happened when transfer failed. We will do it together, don't worry. And then addressing pattern 3, which is problems move forward. The standards FSSC 22000 and ISO 22000 address the problem moving forward through the following clauses. Clause 8.5.1.5, which is control of non-conforming outputs, requires stopping problems, not passing them. Clause 8.9.2, which is monitoring and measurement of processes, requires detection of problems at each stage. and clause 8.9.4, which is verification related to monitoring and measurement and requires confirmation problems are stopped. And then also preventing the problem moving forward is addressed in the standard of SQF code through the following elements. Element 2.7.2, product, which is product release, requires explicit authority to stop the problem. And then through the elements 2.7.3, which is non-conforming products, requires segregation and disposition. And then through elements 2.7.4, product withdrawal and recall, which addresses problems that move forward. And then in BRCG Global, BRCGS or BRC Global Standards, it addresses prevention of problem moving forward through the following clauses. First, through clause 3.h, which is non-conforming products that requires prevention of forward movement of the problem, and clause 3.9, product release, which requires verification before release, and clause 3.10, which is incident management that requires response where problems move forward. Implementation tips here. Establish clear authority to stop production at each stage, make stopping problems easier, then passing them forward. Wait, establish a clear authority. We will do it together anyways, but establish a clear authority to stop production at each stage. Make stopping problem easier, then passing them forward. Measure and reward problem detection, not just throughput. Track where problems are caught versus where they should have been caught. Okay. Now, let's see addressing pattern 4, which is evidence becoming symbolic. We address them through clause FSSC 22000 and ISO 22000 through following clauses. Clause 9.1.1, monitoring, measurement, analysis, and evaluation, addresses evidence prevention from becoming symbolic through requirement of evidence to be analyzed and not just controlled, and also through clause 9.2, which is internal audit that requires verification that evidence reflects reality, and also through clause 9.3, which is management review that requires review whether evidence is meaningful or not. Then we address also prevention of evidence becoming symbolic through SQF code following elements. Through element 2.4.3, which is verification activities that requires confirmation evidence must connect to reality, and also through element 2.5.1, which is validation that requires verification that controls actual work, and also through element 2.5.2, which is monitoring that requires ensuring monitoring is meaningful. Also, with BRCGS or BRC Global Standards, we address through the following of prevention the the evidence from becoming symbolic through the following clauses. Clause 3.4, which is internal audit that requires verification, evidence validation, and also clause 3.5.4, which is supplier performance monitoring that requires confirmation of supplier evidence is real and applicable, and also clause 3.11, which is traceability that requires testing whether records reflects the reality. The implementation tips here to prevent evidence from becoming symbolic is the following. Regularly verify that evidence reflects reality. Don't just check the monitoring records or if the monitoring occurred or not. Verify that monitoring detects the actual problem. Don't just review corrective actions. Verify that they were effective. And don't just collect supplier COAs. Verify that they are accurate. Now, addressing pattern 5, which is pressure wins, clause FSSC 22000 and ISO 22000 address prevention of pressure wins through the following clauses. through clause 8.2, which is prerequisite programs that requires establishment of baseline control that must work under pressure, and also through clause 8.5.4, which is validation that requires confirmation controls work under actual operation conditions, and then through clause 8.8, which is verification that requires ongoing confirmation that controls maintain effectiveness. We address that also to prevent pressure from winning through SQF code following elements. First, through elements 2.4.4, which is food safety plan, that is required the design control for real world condition, and through element 2.5.1, which is validations that tests control under pressure, and then through element 2.5.3, which is internal audit that assesses performance during various conditions. And BRCGS, we address the prevention of pressure from winning through the following clauses. Through clause 2.6, which is contingency planning that requires preparation for pressure situation. And through clause 4.3, which is cleaning and hygiene that requires design cleaning that works under pressure. And then through clause 4.10, which is equipment that requires specifies equipment that maintain function under stress. The implementation here of preventing pressure wins through the following. Design controls assuming pressure will occur. Test controls under simulated pressure. Identify which control failed first under stress and strengthen them. Build redundancy for critical controls. Make it impossible to skip critical steps and not just unlikely. The cross pattern requirements here. Management commitment. All standards require management commitment through the following. Prevent normalization by monitoring external perspectives. Ensure resources for interface management. Provide authority to stop problems. Demands meaningful evidence. Design system for real-world pressure. And also continuous improvement through the management. The continuous improvement is required through all the standards by following. Detect slow failure through trend analysis. Identify interface gaps through system review. Reveal where problems move forward. Question whether evidence is meaningful, and strengthens decisions based on performance under pressure. The integration principle here, these standards clauses are not separate requirements. They are an integrated systems that prepares systems for preventing failure patterns, implementing them actually with the understanding, and they become powerful tools for systematic failure prevention. Now let's explore the practical example here for implementing early warnings. The real-world implementation here for detecting patterns. First, slow failure normalization. All right. Now, note here, this approach has been successfully implemented across diverse operations. It has been implemented through data processing for detecting equipment degradation. It has been implemented in small-scale products packers for monitoring water quality, and it has been implemented in spice importers for tracking moisture content trend, It has also been implemented in seafood processors for monitoring temperature control drifts, and it has been implemented in bakeries for detection of allergen cross contamination patterns. These principles are universal, guys. Again, let's remember the specific metrics vary by operations, but the principle never changes. Principles are universal. Now, let's address this first pattern first, the normalization. The challenge here, your facility monitors data shows gradual drift in critical control point. Individual readings are within its specification, but the trend is concerning. How do you detect and interpret these patterns before it becomes catastrophic? Let's do it together. Step one, establish baseline performance. The action required here, collect 6 to 12 months of historical data for critical control point, then calculate a statistical baseline that include means, standard deviation, and control limits, and then identify normal variation versus concerning trends. Okay? Once you have done that, then document what good look like, not just what acceptable look like. Let me explain an example. Pasteurization temperature monitoring. You will do the following. The specifications, you have 72 degrees Celsius as a minimum, and the historical means is at 75.2 Celsius degree, which is good. And the historical standard deviations is 1.1 degrees Celsius. And the normal range here you have between 73.0 to 77.4 degrees Celsius, which means that's plus or minus standard deviation and not a control limit, right? Now, step two, implement trend detection. What you need to do that first, use statistical process control, SPC, charts, and not just specification compliance. Secondly, establish rules for concerning trends. Okay? The rules should include A, 7 consecutive points trending in one direction. B, 2 out of 3 consecutive points beyond 2 standard deviation on the same direction of the center line. Okay. Thirdly, or C, 4 out of 5 consecutive point beyond 1 standard deviation on the same direction of the center line. That's clear, right? Then D, any point uh, beyond 3 standard deviation. Those are the rules. Okay. Now, here the lower thresholds indicate early warning, but the higher threshold indicates confirmed stability. This is clear, right? Now, example, your pasteurization data shows the following. Week 1 to week 4, the mean is 75.2 degrees Celsius, right? So that's normal. Now, week 5 to week 8, the mean now dropped a little bit to 74.8 degrees Celsius. That's slight decrease, right? Now from week 9 to week 12, the mean dropped again from to 74.3 Celsius. That's continuing decreasing now. Okay. Then in week 13 to week 16, the mean drop again to 73.9 degrees Celsius. Now you have consecutive weeks trending down. Okay. From week 5 to week 16. Okay. Now, the trigger here, even though all readings are above 72 degrees Celsius, which is your minimum specification, the trend trigger investigation. Now, step 3, create escalation protocol. The action you need to create escalation protocol here are the following. You can categorize that into 3. First, establish clear escalation based on trend severity. The level 1 escalation is awareness, which is a minor trend drift. What do you do here? The trigger here for level 1 escalation, it means you have 5 consecutive points trending, okay? And the action that we require for you here for level 1 escalation is to notify the supervisor or increase monitoring frequency, okay? The third here is the timeline. Investigate within 24 hours. Within 24 hours, the monitoring must be done, the investigation, and find the root cause. Okay? Then the authority level here is supervisor. He can own this or she can own this. Now, level 2 escalation, which is investigation, and this is will be the moderate trend. Okay? What happened here? The trigger is 7 consecutive points trending or approaching one standard deviation from the mean. Okay? The action required here is root cause investigation and maintenance review. This is level 2 escalation. The timeline here it must be completed within 24 hours because it's more critical now. And the authority here is quality manager level, is owner of escalation level 2. The level 3 investigation is the intervention, the severe trend. Okay? The trigger here for severe trend or level 3 escalation is the trend approaching a specification limit or 10 consecutive points trending. Okay? The action here required is immediate investigation and potential product haul all here. Okay, to stop the production and start immediate investigation. The timeline here, investigation must be carried out immediately. This is now severe trend. The authority level here could be a plan manager, director, okay? This is the authority level here. Example application. With 13 data, trigger level 2 escalation, which is 7 consecutive trends, right? Now, the quality manager, first the quality manager initiated the investigation, then they discovered temperature probe calibration drift. Then probe replace and calibration was done, and the trend reversed to normal range. Okay? The step 4, now that's done. Let's move to step 4, which is external perspective. You always need this and always remember that. This is where the auditors, the consultants come to the play, even the management, actually. Okay? The actual requirement here to implement external perspective are the following. First, schedule quarterly review by personnel not involved in daily operation. Could be from different department also, or different. If your organization is multi-sites or multi-location or facilities, this will be great. You can bring another person from the other side to come and conduct here quarterly. Okay. Secondly, compare current conditions to historical baseline. Always remember that, not the recent performance. Thirdly, solicit feedback from new employees. Always, it's very critical here. New employees have fresh eyes. They have fresh eye. They always say that, right? So because they see what the veterans don't see. Thirdly, to implement external perspective. Fourthly, use external auditors to identify normalized condition. Example, quarterly review reveal the following. If you implement that, let's assume you implement the above and the following are what you found. First, 3 different controls points showing similar drift patterns, all within the specification, yes, but trending toward the limits. The patterns invisible to daily operation is normalized, but the external reviewer identifies the systematic calibration issue. So always incorporate the implementation of external review. Now let's move to step 5. Create feedback loop. Okay, the action required here for feedback loop creation. First, document what trends are detected and how they are resolved. Secondly, track effectiveness of interventions. Thirdly, analyze positive trends that didn't indicate problems. Okay, then refine trigger points based on experience. Example metrics, trends detected, let's say 12 per quarter, and trends required interventions 8 per quarter, and trends prevented from reaching specifications limits, let's say 8 per quarter, and false positive trends, let's say 4 per quarter, acceptable rate. Now, the implementation timeline here will be as following. The first months, collect and analyze historical data, then establish baseline and control limits, then train staff on SPC concepts. In the second months, implement SPC charts for top 5 critical control points, then establish escalation protocols, and then assign responsibilities. In third months, expand to all critical control points, then conduct first quarterly external review, and then refine trigger points based on initial experience. And from fourth to sixth months, monitor system effectiveness and adjust protocols as needed, and then document prevented failures. The common pitfalls here to avoid during the implementation. The first pitfall is setting triggers too sensitive. The results here, excessive false positive alarms, and it will cause alarm fatigue, and people will start ignoring it. So the solution here is to start conservative and tighten based on experience gradually. Okay. Secondly, second pitfall is collecting data but not analyzing it. The results here, if you don't analyze the collected data, the trend exists in data but aren't detected. Solution, automate analysis and alerts. There are a lot of software that can help you nowadays. Uh, the third pitfall is detecting trends but not acting on it. The results of doing so here is warning systems become symbolic. Nobody care again. The solution here is to tie detection to mandatory escalation. Okay. The fourth pitfall to avoid is comparing to recent performance. The results here, it will normalize drift. The normalized drift remains invisible. So solution is to always compare to historical baseline. The success indicators of the implementation include the following. You know your early warning system is working when the following happen. First, trends are detected and resolved before reaching specification limits. Secondly, staff proactively report concerning patterns, and then external reviews confirm that internal detections is effective, and also you can demonstrate prevented failures, not just detecting failure. The goal here, not to eliminate all variations because that's impossible, but to detect concerning patterns early enough to investigate and correct before they become catastrophic. This system interrupts pattern one by making gradual drift visible and actionable. Now, the integration principle, early warning systems detect failure before it occurs. This is more effective than reacting to problems after critical limits are exceeded. Now, the practical examples here, implementing interface control. Okay, let's do the practical implementation. The real world implementation for preventing pattern two. So I hope the pattern first, the first pattern was clear. So there was a noise in the background. Let's start again. Practical example, implementing interface control. The real world implementation for preventing second pattern, which is the interface failure. Please note, interface failure occurs across all supply chain configurations that include global spices supply chain. It happened between farmers and trader, and between trader and processor, and between processor and manufacturer. And also it happens in dairy corporations from farmers to collections to processors to distribution, all these interfaces in the middle. And then it happened also in seafood cold chains from vessel, processor to distributor, retailer, each interface here, the failure happened. And also it happened in fresh produce between grower and packer, and between packer and distributor, and between distributor and seafood and food service. And also it happened in co-manufacturing relationships between brand owners and contract manufacturer. Now, this example focuses on supplier receiver interface, okay? But the principles apply to all handover points, but we will focus now in supplier to receiver interface to demonstrate clearly. The challenge here, your facility receives ingredients from 20 suppliers. Critical information about handling requirements, contamination risks, and processing history doesn't consistently transfer with shipment. How do you establish effective interface control here? Let's do it together. The standard requirement first, ISO 22000-2018 class 8.4.2. The requirement there is information for supplier. What does it state? The requirement, organization shall ensure that adequate food safety related information is available to enable suppliers to understand the food safety hazards that must be controlled the measures and the measures to control them. Now, this requirement supports the plan and do stage of ISO 22000 PDCA cycle, ensuring upstream control are understood and verified. Okay? Now, let's do it step by step implementation. Step one, map all interfaces. Mapping interfaces prevents hidden handovers points where responsibilities might be unclear, a common root cause of contamination or traceability failure. So first we need to map all the interfaces. The action requires to map all the interfaces, identify every point where controls responsibilities transfer. Okay? Identify every point where the control responsibility transfers. The, let's start with external interfaces. You have between suppliers and you're receiving. Let's assume you have 20 suppliers. You have to identify all these interfaces. Then you have between your shipping and customer receiving. Let's assume you have 15 customers. Here, also that interface, you have to map it out. And then between your facility and co-manufacturer. Let's assume you have three partners. So you have the window there, the interface to be handled. And then the other interface, external interface, include between your facility and the third party laboratory. That handover also need to be mapped. And between your facility and the logistics provider, let's assume you have multiple carriers. Those windows also need to be mapped out, okay, as external interfaces. Now let's go to the internal interface. You map out all the internal interface, including between receiving and storage, between storage and production, between production and packing, between packing and shipping, between shift A and shift B, and if you have three shifts, that means between morning shift and afternoon shift, and between afternoon shift and night shift, and from night shift to morning shift, and the side. Okay, so you have those windows there. And then between production and quality, multiple handovers throughout the day there, right? Or throughout the operations. And also between maintenance and production, equipment handover, the cleaning and the permit and all that. You have to map that. Example, focus is supplier receiving interface. You remember between supplier and between receiving interface. There's step 2 here now. You need to define the critical information transfer here. And our focus, again, is between supplier and receiving. The action requires here to define the critical information to be transferred in this interface. And for each interface, it specifies exactly what information must be transferred. For ingredient shipping, for example, we must transfer between supplier and interface, right? For ingredient, we transfer product identity. Information must include specific products names and code, uh, lot or batch number, production date, and expiry date or best before. Okay, those are the information with the product identity. And then the information also needed is the safety information. Safety information should include, for example, allergen status, whether it contains allergen, may contain, free of allergen, all that need to be indicated. And then microbiological test results and chemical test results, including pesticides and heavy metal, etc., and also the physical hazard control applied. Those are the safety information that must be included there. Thirdly, the handling requirements here must include the following information: temperature requirements during the transport, time temperature history during the shipping, special handling requirements, and storage requirement upon receiving. These information also must be included in this interface. Okay. Now, example for that, let's say handling requirement, frozen berries must remain below minus 18 Celsius, for example, during the transport. And receiving must verify the temperature log. Okay, so you verify if it was maintained. That's just for example. Now the processing history also have you have to receive the information of the process history, which should include the following: process steps applied, like heat treatment, ingredient, etc. Okay, and also you have to receive in processing history critical control points records, any deviation or corrective actions, and previous rejections or quality issues. All this need to be included as information of history of processing history. And then also you need information about traceability here in this interface. That must include the information about traceability, supplier lot number, raw material source information, previous processing location, chain of custody documentation. Okay, so you need those information. Now we move to step 3, which is to establish the transfer mechanism. How do we establish it? First, design how information will physically transfer. Okay, but there is no one size fit all. Uh, the right mechanism depends on the digital maturity of your organization or your supplier capability or your capability and regulatory environment also for where you operate. But let's say now for the designer how to inform the physical transfer, option 1, integrated documents. How do you do that? Supplier provides comprehensive shipment documents. Second, documents travel with products. Thirdly, receiving verifies documentation before acceptance. And fourth, the documentation is reviewed and filed. The example template, create a standardized shipment information sheet, okay? Which must be requiring the following: all critical information in standardized format, supplier signatures confirming accuracy, and space for receiving verification, and clear escalation if information is incomplete. The second option, which is digital information transfer, should include the following: supplier enters the information into shared system. Let's say sometimes even email, right? And then information is available before product arrives. Thirdly, receiving verification, receiving verifies products matches digital information. And then fourthly, system flags incomplete information. The example implementation here include the following: supplier portal for entering shipment data, okay? And then automatic alert if required fields are incomplete. Thirdly, receiving app that verifies product against digital records. And fourthly, automation escalation for discrepancies. Now, the third option, you have first option physical, the second option digital. The third option is hybrid approach. How do you do that? First, critical safety information transfers digitally, advance notice. Secondly, supporting documentation travels with uh, products. Thirdly, receiving verifies both digital and physical information batch. And fourthly, discrepancy trigger hold and investigation. The fourth step here is verified information transfer. The action required here, don't assume information transferred correctly. It's verified it. The receiving verification protocol. Before uploading, do the following. Shipment documentation received and complete. Product identity match purchase order. Temperature requirements maintained during the transport. And visibility, demand, or contamination. Just verify those you before you upload. And during receiving, do the following. Verify that product matches the documentation through visual verification, and then check the lot number that is matching the documentation, quantities matching the documentation, and packing integrity is acceptable. And before you accept also, do the following. All requirement test results present, all the required tests are present and acceptable. Allergen information complete and accurate. Handling requirements understood and feasible. Traceability information complete. And if any verification fail, do the following. Product is held or not accepted into inventory. Supplier is contacted immediately. Missing information is obtained before acceptance. Pattern of incomplete information triggers supplier review. Okay? Now, then you move to step 5. You need to establish the interface ownership here. In order to do that, first, assign clear responsibility for each interface. Secondly, between interface and receiving. No, first, no, wait, let me go back. Actually, you need to establish the interface here. Okay? You do it as the following. First, you need to assign the responsibility for each interface. So between supplier and receiver interface now, the supplier responsibilities here, we have supplier, we have receiving interface. So let's give the responsibility. First, the supplier responsibilities include provide complete, accurate information with every shipment. Ensure information travels with product. Respond within 4 hours to information requested. Or otherwise, this is just an example, but it could be as per the agreed service level in contract with your supplier. And then fourthly, maintain digital records accessible to customer. Your receiving responsibility here, those are the supplier responsibility, but your responsibilities must include verify information completeness before acceptance, communicate requirements clearly to suppliers, provide feedback on information quality, escalate patterns of incomplete information. Okay? The interface manager, your quality team, is the interface manager, and the following are the responsibility. So now we have the responsibility for the supplier and for the receiving, which mainly could be the warehouse or the operation. And now you have the interface manager, who is the quality team, and the responsibilities include monitor information transfer effectively, track incomplete shipments by suppliers, conduct quarterly supplier review, update requirements based on experience. Wait, let me go down here. Let me go back here a little bit to check something. Yes, correction. For correction, the receiving responsibility is also our quality management responsibility. Okay, so the who is now the interface manager here? Because they need to verify the information also. Okay, and they need to release the acceptance. That's the standard operations. Sorry for confusion. Now let's proceed. The step 6, implement interface metrics. And this is how you do it. First, measuring interface performance turns invisible communication gaps into data so that you can do something about it. But the action you need to implement the interface metrics includes the following. First, measure the interface performance. And to measure that, you need key metrics. Include the first key metrics is information completeness. And information completeness requires the percentage of shipments with complete information on the first receipt. The target now is like over 95% of shipment. Let's say this is the target now you set to ensure all the shipments have the complete information. And you have the baseline is the activities that were done before you implement now the current improvement. So let's say the baseline was at 73, but now you set it at above 95. And now you need to track by the supplier. The information accuracy will include that this is the second key. The first metric, key metrics is information completeness. The second key metrics is information accuracy, which should include the following. The percentage of shipment where information matches the product. The target now is above 99% must be accurate. The baseline of accuracy is at 88. This is what was happening before you implement this improvement. And now you need to track by the supplier. The third key metric is response time. You will set the following requirements. First, time to obtain missing information. Secondly, the target you are timing for time to obtain the information is must be under 2 hours. The current baseline, it was done in 8 hours, but now you set it under 2 hours. Tracked by the supplier, okay? And now the fourth interface key metrics is interface failure, and it should include the following information. Number of shipments held due to incomplete information, number of issues discovered after acceptance, but this should have been caught at interface. And third, number of customer complaints related to the information gaps. Okay, so that's how you set up the metrics. Now let's move to step 7 to create the feedback loop, okay? And feedback loop here close the PDCA cycle that we spoke about before. They ensure lessons from suppliers translate into better control next time and with other suppliers also. The action we need here to create a feedback loop. First, we need to use the metrics to drive the improvement. Okay, so monthly supplier scorecard need to include the following: information completeness rate, information accuracy rate, response time to requests, and trend over time. Okay, and quarterly supplier review include review scorecard performance, identity root causes of incomplete information, agreed on improvement actions, and set targets for the next quarter. Example implementation. Let's assume supplier X consistently provides incomplete allergen information. So we did the following. The root cause, no, first, the root cause for that, their system doesn't capture may contain allergen information, okay? The may contain, they don't capture that. To improve the action, we need, we set the action for supplier to update their system, okay? And the verification here, we need to verify that the next shipments have to mention, we need to monitor, and the next shipment, while we are monitoring them closely, they have to confirm that all of them are containing may contain. In the result is completeness improvement from 60% to 98%. Okay. Now, the BRCGS class 3.51 supplier approval. How does it? It requires the following three keys. First, it requires suppliers to demonstrate capability to provide required information, and also it includes information transfer requirement in supplier agreement, and it also monitors supplier performance on information quality. And then the implementation timeline here. The first month, map all the interfaces, define critical information for top 5 suppliers, create a standardized documentation template. In the second month, implement verification protocols for top 5 suppliers, train receiving staff, and establish metrics and tracking. The third month, expand to all suppliers, conduct first monthly scorecard review, and identify problem suppliers for focus improvement. In months 4 to month 6, refine based on experience, conduct quarterly supplier review, demonstrate improvement in interface performance, common pitfalls to avoid once you are in the while implementing. Those are following are the common pitfalls to avoid. The first pitfall is assuming suppliers know what you need. The solution here provide explicit or clear written requirement to the supplier. The second pitfall is accepting incomplete information from the supplier and saying things like, just this time, next time they will provide. No, no. Solution here, enforce requirements consistently, and suppliers will be alerted knowing that you don't, you don't compromise the quality requirements. The third pitfall is collecting information but not using it. The solution here is to demonstrate how information drives decisions. The pitfall number 4 is blaming suppliers without clear requirements. Solution here, ensure requirements are clear, reasonable, and documented. Okay. The success indicators there for your implementation, you know your interface controls are working when the following happen. More than 95% of shipments arrive with complete, accurate information. Issues are caught at receiving, not discovering later in the production. Suppliers proactively communicate change or issues. You can trace critical information through the entire supply chain, and customer complaints related to supplier information approach to zero. The goal here is to eliminate the gap between where suppliers' controls end and where your controls begin. Make the interface explicit or clear, make it managed and verified. This prevents pattern 2 by ensuring control doesn't break down at handover. Okay? Now, let's move for the assessment. Assessment, identify failure patterns in your system. Okay? Before moving to module 4, complete the assessment to identify which failure patterns uh, pose the greatest risk in your system. Okay, be honest, and this is your benefit. It's not compliance. Okay, just be honest with yourself. Now, the first pattern assessment is low failure normalization. Okay, rate your systems between from 1 low risk all the way until 5, which is high risk, by doing the following. Ask yourself those questions. Okay, We have monitoring data trending toward specification limits over time. Is that true? Assess that. The staff use phrases like, it's always been like that, or that's normal for us. Okay. We have the other thing to assess. Check. We have. Let me go back just to make it clear for those who are listening to the audience without video. Pattern one. Let's start with the assessment here. Assessment. Identify failure patterns in your system. Before moving to Module 4, complete this assessment to identify which failure pattern pose the greatest risk to your system. Be honest, this is your benefit, not for compliance. Pattern 1 assessment. Pattern 1 is slow failure normalization. Okay? Now, rate your systems from low risk by 1 or high risk by 5 and in between. Rate your system against the following. First, we have monitoring data trending toward specification limits over time. 2, staff use phrases like, it's always been like that, or it's normal for us. 3, we have recurring corrective actions for similar issues. 4, new employees express concerns about conditions that veterans consider normal. 5, we have a growing backlog of minor maintenance issues or maintenance items. 6, our trend analysis is infrequent or superficial. 7, we compare current performance to recent performance, not to historical baseline. If you scored more than 3 items as high risk, pattern 1 is your primary vulnerability. Implement trend analysis tool, establish external review process, and create mechanism for new perspective. Okay. Now let's move to pattern 2 assessment. Pattern 2 is interface failure. Rate your system against the following with the same criteria above. 1 is low risk and 5 is high risk and in between. Critical. Now you are starting to assess the pattern 2, which is interface failure. Start with critical information doesn't consistently transfer with product. Your answer to that. We have unclear ownership of activities between departments or companies. 3, different parties have different understanding of specifications. 4, we experience communication gap during shift change. 5, supplier documentation doesn't match our expectation. 6, we have gaps between where one party's control and another begins. 7, we assume someone else handling interface activities. Again, if you score more than 3 items as high risk here, that means pattern 2 is your primary vulnerability. Map all interfaces, clarify ownership, establish verification protocols, and implement interface specific controls. Now let's assess pattern 3, which is problem move forward. Rate your system against the following. Stopping problems is more difficult than passing them forward. As 1. 2. We have incentives that reward throughput over quality. 3. Staff use phrases like, the customer will handle it, or we can blend it out. 4. Our rework and reprocessing rates are increasing. 5. We have complex approval processes for rejecting materials. 6. Production staff lack clear authority to stop production. 7. Customer complaints reveal issues that should have been caught internally. If you score more than 3 items as high risk here, pattern 3 is your primary vulnerability. Establish clear stop authority, make rejection easier than acceptance, and align incentives with problems detection. Now let's assess the fourth assessment, the fourth pattern, which is evidence becoming symbolic. Rate your systems against the following. We collect monitoring data, but rarely analyze it. Corrective actions are documented, but effectiveness is not verified. We focus on completing paperwork rather than verifying control. Records doesn't trigger action even when showing problems. We measure compliance by paperwork completion, not safety outcomes. Audit findings are closed without confirming actual resolution. We, we have increasing documentation, volume with increasing utilities. If you score 3 plus items as high risk here, pattern 4 is your primary vulnerability. Implement random verification of records against reality, ensure evidence trigger actions, and connect documentation to decision making. Now let's assess the fifth pattern, which is pressure wins. Assess your systems against the following. Critical controls depend on human attentions during stress. We have no redundancy when primary systems fail. Procedures assume ideal conditions. Critical steps can be skipped under pressure. We have increasing exceptional procedures during busy periods. Performance degrades noticeably during peak hours or peak seasons. Incident rates increase during high pressure periods. If you score more than 3 items as high risk here, pattern 5 is your primary vulnerability. Redesign controls for pressure conditions, build redundancy, automate critical controls, and stress test your system. The overall system assessment, if you multiply, if multiple patterns score high risk for you, your system has systematic vulnerability, and you should prioritize based on first, which pattern has caused problems in the past, second, which patterns would have the most severe consequences, and thirdly, which pattern is easiest to address with available resources. If no pattern is scored high risk, either your system is exceptionally well designed or you are not being honest with yourself. Consider the following then. Having external parties complete this assessment for you, reviewing recent incidents through the lens of these parties, and asking frontliner staff about these patterns. They often see what management doesn't see. Action planning. If your high risk patterns, identify specific warning signs to monitor, establish detection tools and thresholds. This is for your highest risk. Again, the action plan for your highest risk pattern. Okay, do the following. First, identify specific warning signs to monitor. Second, establish detection tools and thresholds. Thirdly, create response uh, protocols. Four, assign responsibility for monitoring and response. Five, set time for implementation. Six, schedule review uh, of effectiveness. The goal here is not to eliminate all risk, as we said earlier, it is possible, but to detect and interrupt failure patterns before they cause harm. Focus on your highest risk pattern first, then expand to others. Okay? So before Module 4, document your assessment results because Module 4 would provide a specific implementation guide for addressing the patterns you have identified. Now let's explore the cross-reference failure patterns prevention through our standards. We'll run a quick reference here showing which standard clauses help prevent each failure pattern. First, we have the first pattern, which is prevention of a slow failure normalization is prevented through ISO 22000 clause 9.1.1, which is monitoring, is prevented through ISO 22000 clause 9.3, which is management review, and is prevented through FSSC 22000 clause 2.5.14, which is testing, and is implemented through BRCGS clause 4.10, which is inspection. That's pattern one, okay? Prevention. Pattern two, prevention. Prevention of interface failure is addressed through the following standards. ISO 22000 class 7.4, which is external communication. ISO 22000 class 8.4.2, which is supplier management. BRCGS class 3.5 for supplier management. And SQF module 2.5.3, which is supplier approval. The third pattern, prevention, the problems moving forward. Prevention is prevented through the following standards. It's prevented through ISO 22000 clause 8.6 for traceability, ISO 22000 clause 8.8 through corrective actions, BRCGS clause 3.9 for product recall, and SQF module 2.6.2 traceability. The pattern for prevention here, symbolic evidence, okay? Uh, Prevention of the symbolic evidence through the standards as following. First, ISO 22000 through clause 9.2 for internal audit, ISO 22000 through clause 9.3 for verification analysis, and FSSC 22000 clause 2.5.14 testing effectiveness, and BRCGS class 2.12 internal audits. Finally, the fifth pattern, prevention of pressure effects, is prevented through the following. FSSC to the 2000 class 2.5.1 for food defense, and is prevented through FSSC to the 2000 class 2.5.2 food fraud, and is prevented through BRCGS clause 5.4 for food defense, and through SQF module 11.2 for food defense. Every standard requirements here serves purpose in preventing predictable failure patterns. Effective implementation requires understanding these connections. Now, why understanding failure pattern is critical for every role? Let's see why. First, regardless of your position in the food system, understanding failure patterns enable more effective risk management. And here's how this knowledge applies to specific roles. For food safety managers and quality directors, patterns recognition enables proactive management of the following. First, you will be able to detect slow failures through trends analysis before specifications are violated. You will be able to identify interface gaps in supplier relationships and internal handovers. You will, you will be able to recognize when problems are being passed forward rather than stopped. And you will be able to distinguish between meaningful evidence and symbolic documentation. And finally, the recognition of this pattern will facilitate your proactive management to design systems that maintain control under operational pressure. The practical application, instead of reacting to audit findings, and here, still for quality managers and directors, instead of reacting to audit findings, you can do the following. Implement early warning systems that detect patterns months before failure. Design interface controls that prevent gaps in supplier management. Create incentives that reward problems detection, not just throughput. Verify that your evidence systems connects to reality, not just compliance. Build capacity to observe seasonal peaks without control degradation. And for operations and production managers, pattern understanding prevents production disruption through the following. You will be able to recognize when normal operations are actually normalized deterioration. You will be able to identify when production pressure is revealing design weakness. You will be able to understand why stopping problems saves money compared to passing them forward. And you will be able to see how interface failure between shifts or departments create quality issues. The practical application here, first, instead of fighting fire, you can do the following. Once you understand these patterns, you can implement trend monitoring that prevents equipment failure during peak periods. You can design shift handover protocols that prevent information loss. You can create a stop authority that prevent problems from reaching customers. And you can build production systems that maintain quality under pressure. And finally, you can reduce rework and waste by catching problems earlier. For procurement and supplier quality, pattern recognition transforms supplier management through the following. You can identify when supplier problems are being passed forward to you. You can recognize symbolic evidence in supplier documentation. You can detect slow failure in supplier performance before it causes your failure. And you can understand interface gaps in supplier receiver relationship. The practical applications for you here, instead of receiving suppliers management, instead of reactive supplier management, you can do the following. Design supplier interface that ensure critical information transfer. You can also implement supplier scorecard that detect patterns, not just points failure. And you can create verification systems that confirm evidence reflects reality. Also, you can build supplier relationship that encourage problem reporting, not hiding. And you can prevent supplier issue from becoming your customer complaints. Now, for regulatory and compliance personnel, pattern understanding enhances audit effectiveness through the following. You will be able to look beyond documentation to detect actual control. You will be able to recognize when evidence has become symbolic. You will be able to identify normalized conditions that indicate slow failure, and you will be able to understand why certified systems still experience failure. The practical applications here, Instead of checklist audit, you can do the following. You can design audits protocols that detect failure patterns, not just nonconformities. You can ask questions that reveal normalizations and interface gaps. And you can verify that corrective actions addresses pattern, not just individual incidences. And you can assess systems performance under pressure, not just ideal conditions. And you can value added insights that prevent failure. For executive leadership, pattern understanding informs a strategic decision through the following. You can recognize that food safety failure are predictable and preventable. You can understand why blame culture weakens the systems. And you can see how production pressure reveals design weaknesses. And you can appreciate why certification is necessary but not sufficient. Practical application for you. Instead of reacting crisis management, you can do the following. Invest in system design that prevent failure, not just respond to them. Create organizational culture that reward problem reporting. Allocate resources to address failure patterns systematically and build competitive advantage through superior food safety performance and protect brand reputation through proactive risk management. And for technical and R&D personnel, pattern recognition improves product and process design through the following. First, design products and processes that resist failure pattern. Secondly, understand how interface failures occur in complex formulation. Thirdly, recognize when evidence systems don't reflect actual control. And fourthly, anticipate how product you can anticipate how production pressure will affect new processes. Practical application for you. Instead of designing for ideal condition, you can do the following. You can build failure pattern resistant into new product development. You can design processes with explicit interface controls. And you can create verification systems that ensure evidence reflects reality. And also you can test new processes under simulated pressure conditions, and you can prevent problems in design phase rather than discovering them in production. And for the training and human resources, pattern understanding transforms training effectiveness into following. You can teach, no, you can teach why failure occur, not just where procedures to follow. You can help personnel recognize warning signs of failure patterns, and you can create culture where reporting problem is rewarded, not punished. And you can understand that most failure are system issues, not individual issues. The practical application for you, instead of produce focused training, you can do the procedure focused training. You can do the following. First, you can develop training that build patterns recognition skill. You can create psychological safety for problem reporting. You can design onboarding that captures new employees' perspective. And you can build organization capacity for continuous improvement. And you can reduce turnover by creating meaningful empower role and empowering roles. And for maintenance and engineering, pattern recognition prevents equipment related failure through the following. You can detect a slow failure in equipment performance through trend analysis. You can recognize when temperature fixes are normalized into parameter problems and permanent problems. You can understand how deferred maintenance creates failure patterns, and you can see how production pressure affects maintenance effectiveness. Practical application for you: instead of reactive maintenance, you can do the following. Help predictive, implement predictive, you can implement predictive maintenance based on trend analysis. You can design equipment that maintains function under pressure. You can create maintenance schedule that prevents normalization of deterioration. You can build redundancy for critical systems, and you can prevent equipment failure during peak production periods. And for the universal benefits, regardless of role, regardless of your role, understanding failure patterns enable you to do the following. You can see earlier, check warning signs before they become crisis, and you can think systematically. You can understand how patterns interact and reinforce each other, and you can act proactively. You can prevent failures rather than react to them. And you can communicate effectively. You can explain risks and solutions to others. And you can build better design systems, processes, and practices that resist failure. The competitive advantage here: organizations where personnel at all levels understand failure patterns, the following happen: experience fewer recall and incidences, responds more effectively when issues occur, build stronger supplier and customer relationships, create more resilient operations, protect brand reputation more effectively, and reduce costs associated with failure and rework. When happen to organizations where personnel at all levels understand failure patterns. Your role, your responsibility. Whatever your position, you now have knowledge that most food safety professions lack. You understand how food safety really fail. This knowledge creates responsibility. So apply in your daily work. Share it with your colleagues. Use it to improve your systems. Maintain vigilance against normalization and act on warning signs before they become catastrophes. The patterns are universal, the application is role specific, and the responsibility is shared. Let's see here what happened. Okay. Now, what failure patterns mean for system design? Let's explore together. We are almost done. Understanding failure patterns completely change how food safety systems must be designed. This is not implementation improvement. This is not incremental improvement. It is a fundamental rethinking. Okay. Now, traditional approach versus pattern resistant design. Let's explore. In traditional approach, the design is done for compliance, and the focus there is to meet the standards requirement. The measures there is documentation completeness, and the assumption there is following procedures create safety. Is that the following create safety? And they react is reactive by design because they respond when specifications are violated. But now, if you look at pattern resistant design, is designed for performance. The focus here is to prevent failure patterns and the measure leading indicators of pattern emergence. You see, the assumption here, pressure and drift. are inevitable and is a proactive design because it detects and interrupts patterns before the harm. System design implication from static to dynamic monitoring. The- In, in traditional approach, monitoring against fixed specifications, alert where limits are exceeded, and focus on point-in-time compliance. But in pattern-resistant design, monitor trends. We monitor trend, not just points. Alert happen when patterns emerge. Focus on trajectory and direction and detect drift before limits are approached. Example here in tradition, temperature is at 72 degrees Celsius. It meets the minimum, so it's acceptable. But in pattern resistance, temperature has decreased zero point 0.2 degrees Celsius per week for 8 weeks. Investigation occur, and we prevent problem there. Two, from process control to interface management. Let's see, in traditional, how does that happen? It's design controls for internal processes. Uh, s- it assumes supplier certifications means control, and it focuses on what happens inside your facility. That's the traditional approach. In the pattern resistant design, the following happen. Explicitly manage every interface. Every information transfers. Don't assume it. No, no. Verify information transfer and don't assume. That's the requirement of pattern resistant. Control extends through entire supply chain, and interfaces are as critical as the processes. Example, in traditional, supplier is certified, is accepted, their COA are good, we accept that. But in pattern resistant system, we verify the COA accuracy and we confirm the information transfer and we validate supplier control. Okay. Thirdly, from documentation to verification. In traditional approach, the following happen. People collect the evidence of the control, they file the documentation, and they measure it by paperwork completion. But in pattern-resistant approach, the following happen. Pattern-resistant design. You verify evidence. Evidence reflects the reality. You use the documentation to drive action. You measure by control effectiveness, and you randomly verify records against actual conditions. Example, in traditional monitoring records complete, they're completed, files done. But in pattern resistance, monitoring records reveal, are reviewed, trend and analyze actions taken on concerning patterns. Four, from ideal condition, pressure design. In traditional approach, design procedures for normal operation and it assumes procedures will be followed and it reacts the people react to when pressure causes failure. But in pattern resistant design the following happen. It's designed for peak pressure conditions. It's build controls that work when stressed. Test systems that simulated pressure and automate critical controls that can depend on human attention. Now, example, traditional. The traditional approach, they will tell you follow cleaning procedure and assume the time is available. But in pattern resistant, the minimum cleaning time is locked into system and cannot be shortened under pressure. Fifth, from blame to learning. In traditional approach, identify who fail, punish who retains, uh, punish or retrain individual, and assume the problem is solved. But in pattern resistant design, It goes like this: identify patterns enable failure, redesign system to prevent patterns, learn from near misses and close calls, reward problem reporting. Example: traditional worker. In traditional, the worker failed to follow the procedure, retrain the worker. That's how it's following in traditional. But in pattern resistant, if the same happen, procedure fail under the pressure. Redesign procedure to work under stress. 6. From reactive to predictive. In traditional approach, the following happen: wait for problem to occur, respond to specification violation, and react to audit findings. But in pattern resistant design, the following happen: detect warning signs early, respond to concerning patterns, prevent issues before they occur, and use leading indicators, not just lagging indicators. Example: in traditional approach, if the product fail micro test, what happened there? Investigate and correct. But in pattern resistance, if the same problem happen, the environmental monitoring shows increasing pathogens persistence, investigate before the product is even affected. Okay? Organizational implication. Different skills required here. Okay? First, in traditional system, procedure following, documentation completion, and specification compliance. But in pattern resistant system, pattern recognition is required, trend analysis, system thinking, and proactive problem solving. Those are different skills there. Also, different culture are required here. In traditional system, people are compliant focused, blame for failure, procedure driven, reactive. But in pattern resistant system, is performance focused, is learning from failure, and is outcome driven, and is proactive. And here, different leadership also are required. In traditional systems, enforce compliance, punish deviation, and maintain procedure. But in pattern resistant system, you build the capabilities, encourage reporting, improve system, maintain vigilance against normalization also. And also different metrics are required. In traditional system, documentation completion rate, audit scoring, and specification completion. But the metrics for pattern resistant system include leading indicators of failure patterns, trend analysis results, prevented failures, early warning systems effectiveness. Now, investment implication. Pattern resistant system requires investment, okay, in the following. First, it requires investment in technology, automated monitoring and trend analysis, real-time data system and predictive analytics, and interface management tools. Those are the investment needed. And also to invest in people, train in pattern recognition, develop of analytical skills, development of analytical skills, and building systems thinking capabilities, and creating psychological safety for reporting. Also, it requires investment for processes to redesign for pressure conditions, interface mapping and management, and evidence verification system and early warning protocols. And then for cultural shift from blame to learning and reward problem detection and encourage proactive reporting and maintenance external perspective, maintaining external perspective. The return on investment calculation in traditional approach costs are the following: reactive incident response, recall and withdrawal, brand damage, cost loss, regulatory penalties, and litigations. But for pattern resistant approach, the costs are the following: system design investment, technology implementation, training and development, and ongoing monitoring. Now, the difference, the difference here, the pattern resistant system prevents failure that traditional system only respond to. The investment is in prevention is consistently lower than the cost of failure. Now let's look at the example of the Peanut Corporation of the America again to demonstrate this point. What happened there? The cause of uh, let's wait. The cause of failure. The cause of failure in the Peanut Corporation of America include criminal persecution of the executives, company bankruptcy, 9 deaths, 714 illness, thousands of products recall across the industry. Estimated cost was over 1 billion across the supply chain, and the prison sentence for the executives unprecedented in food safety. That could have been prevented by doing the following: acting on positive test results instead of ignoring them. The evidence was documented that they got ignored. And then they could have done the following also: external perspective interrupting normalization. But auditors miss the pattern. And in cultures why those happen, we'll explore in later modules. Thirdly, authority to stop production could have been facilitated and it could have been safe. It could have saved all that. But employees lack power to refuse shipping. And then system design that didn't allow contaminated product to stop, but they don't have physical barriers and they just force the shipment to happen. The strategic choice here, okay? Organization must choose between two options. First option, continue traditional approach, accept the failure will occur and manage the consequences, like the Peanut Corporation of America did. Or option two, invest in pattern resistant design, prevent failure systematically, and build competitive advantage. There is no middle ground here. Failure patterns will occur, and we have seen that. The only question is whether you will detect and interrupt them before they cause harm. The implementation reality here, this is not a quick fix, okay? Building patterns resistance systematically require the following: 6 to 12 months for initial implementation, ongoing investment in maintenance and improvement, cultural change that might take years, and leadership commitment that persists through the challenges. But the alternative, continuing to experience predictable, preventable failure, is more expensive in every dimension: financially, reputationally, and human. The bottom line here: understanding failure patterns change everything about how food safety system must be designed, implemented, and maintained. Organizations that make this shift will prevent failure that their competitors only react to. This is the future of food safety management. Now, connecting failure patterns to standard implementation. Every requirement in modern food safety standards exists as a response to one or more of these failure patterns. Understanding these connections transforms standards from compliance checklists into powerful tools for failure prevention. Why HACCP is required? You ask. Prev- HACCP, let's see why HACCP is required to prevent the slow failure. In principle 4, which is monitoring HACCP, principle number 4, monitoring detects drift before catastrophic failure. Principle 5, corrective actions interrupts problems before they normalize. And principle 6, verifications provides external perspective on normalization conditions. And principle 7, documentation creates historical baselines for trend comparisons. Uh, the prevents patterns too also through the HACCP here, the interface failure. Hazard analysis. Through hazard analysis, identification of hazard at interface, not just within the processes. And also, critical control points can be established at interfaces, receiving and handover. Okay? And monitoring, also through monitoring, the HACCP will prevent second pattern interface failure because it verifies control at interface. And verification also, HACCP could prevent interface failure through verification for confirms to confirm interface control are effective. HACCP also can prevent pattern 3, which is probably move forward through the following. Critical limits defines when problems must be stopped through corrective actions, which requires stopping and correcting, not just passing forward, and verifications, which requires confirmation of problems are stopped and appropriate and at appropriate point. Also, HACCP can stop the fourth pattern, which is symbolic evidence, through the following. Through validation, which requires confirmation controls. Confirmed controls actually work. Evidence reflect reality. Also through verifications, because to test whether monitoring is meaningful, and through record review to ensure documentation drives actions. And also prevent patterns. Uh, the pattern 5 could be prevented through HACCP, and pattern 5 is pressure wins. The HACCP could prevent that through the following. First, through validation, which requires testing, which tests the control under actual operation conditions and through critical limits based on science, not convenience, and through monitoring, which is designed to work under operational pressure. The HACCP Insight. HACCP was developed in response to actual failure patterns in food production. It is not arbitrary. It is a systematic response to how food safety actually fails. Implementing it with that understanding is a requirement. Okay. Now, why prerequisite programs are required? If you ask that, prerequisite programs are required to prevent also all the patterns through the following. Pattern 1 could be prevented through prerequisite program as following. Maintenance programs prevents equipment deterioration. Cleaning program prevents sanitation drift. Calibration program prevents measurement system drift. Pest control program prevents gradual infestation. Also, it will prevent the second pattern, which is interface failure, through the following: receiving program through control supplier interface, storage program through control storage production interface, and shipping program through control facility customer interface. Just let me come back again here. And here, the second pattern to be prevented through prerequisite program. If you have receiving program, you can control the supplier interface between supplier and your receiving, right? And then a storage program, you can control the interface failure there between control storage and production interface. And then you can do the same for shipping program to control between control facility and customer interface. Now, the prerequisite program also can prevent that the third pattern, which is problem move forward. And you can do that by the following suggestions program, physically prevent problems movement, segregation program, sorry, physically prevents problem movement, identification programs, tracks problem to prevent moving forward, rework program controls how problems are handled. And also the prerequisite programs can prevent the fifth pattern, which is pressure winds, through the following design and construction, physical barriers that work regardless of pressure, equipment program, maintain function under stress, utilities program, ensure adequate capacity for peak periods. The PRP inside here, prerequisite, creates the function that prevents failure patterns from emerging. They are called prerequisite because HACCP cannot work without them. Failure patterns will emerge in their absence. Now, why management systems are required? To prevent, let's start by preventing the management systems are required to prevent the patterns. And let's start with pattern one. Management system will prevent it through the following management review, external perspective on normalized condition, and also the slow failure, which is pattern one, could be prevented through internal audit, which is periodic assessment against historical baseline. And also, slow failure could be prevented through continuous improvement, which is a systematic detection and correction of drifts. Now, prevents also the management system are required to prevent the I need to stop this way. Also, prerequisite programs. Just a second here. Let me see what's happening. Sorry, guys, we had a glitch. So let's continue. Uh, Also, prerequisite program can prevent the third patterns, which is probably moving forward through first segregation. I think now we are going back, but that should be okay. Through segregation program, physical barriers, preventing problem movement, and also through identification program by tracking problems to prevent forward movement, and also rework program by controlling how problems are handled. And then it also prevents the fifth pattern, the prerequisite program, prevent through the fifth pattern, which is pressure winds, through design and construction, which is fixed physical barriers that work regardless of the pressure, and equipment program through maintaining functional under stress, and also utilities programs, which is ensuring adequate capacity for peak period. The PRP inside here, prerequisite program, creates a functional that prevents failure. They are called prerequisite program because HACCP cannot work without them. Now let me just move forward to where we stopped so that we don't keep repeating. We reached to the management earlier. The management continuous improvement. Okay, so the management also can prevent the third pattern, which is problem moving forward through the following non-conformities management, which requires stopping the problem and products release, which with explicit authority to stop the problem, and also though with incident management, uh, with response when problems move forward. And management also can prevent the fourth pattern, which is symbolic evidence, through the following: monitoring and measurement by ensuring evidence is meaningful, analysis and evaluation by connecting evidence to actions, and verification activities by confirming evidence reflects reality. And also, management could prevent fifth pattern, which is process pressure wins, through the following: resources management by ensuring adequate capacity, competence requirements by maintaining capability under pressure, and also through contingency planning by preparing for pressure situation. The management systems inside here, management systems provide the organizational structure that detects and responds to failure patterns, and without them, even good technical controls will fail under organizational pressure. Why traceability is required? Now let's move to the traceability. Traceability enables detection of all the patterns through the following: pattern 1, through historical data, which enable trend analysis; pattern 2, through revealing where information is lost at interface; and it could also prevent the third pattern by showing where problems move forward undetected; and through pattern 4, also it can stop pattern 4 through testing where evidence reflects reality; and also it can stop pattern 5 um, through identification which controls fail under pressure. The traceability inside here, traceability isn't just for recall, it is a diagnostic tool that reveals failure patterns in your system. So now let's move to the validation and verification. Why are they required here to stop those patterns? First, the validation and verification can stop this pattern 1, symbolic evidence, through the following: the validation confirms control actually work, not just documented; verification tests whether evidence reflects reality; and review ensures evidence drives action. It can The validation and verification also can prevent pattern 2, which is pressure wins, through the following: validation tests control under actual operation conditions, and verifications confirm controls maintain effectiveness under pressure. The validation and verification inside here, the requirements exist because evidence can become disconnected from reality. But here the validation and verification force periodic reconnection. Why supplier management is required to prevent those patterns? First, the supplier management could prevent pattern 2, interface failure, through the following: supplier approval establishes interface requirement; supplier monitoring verifies interface performance; and supplier communication ensures information transfer. And also, the supplier management prevents pattern 3, which is problem moving forward, through the following: supplier requirements defines when suppliers must stop problems; and supplier verifications confirms problems are stopped upstream; and prevents supplier management also prevent pattern 4, symbolic evidence, through the following: supplier audits verifies suppliers evidence reflects reality; suppliers testing confirms suppliers documentation is accurate; and the supplier management inside here, your supplier's failure patterns become your failure patterns. Supplier management extends your patterns detection and prevention upstream. Now let's move to the training to stop the pattern. Why training is required? It prevents all the patterns through the following. It prevents pattern one, training personnel to recognize normalization. The second, patterns, the training ensures understanding of interface responsibility. And it prevents pattern five because training builds capability to stop the problem. And it prevents pattern four because training teaches difference between meaningful and symbolic evidence. And it prevents pattern five because training prepares personnel for pressure situation. The training inside here, training isn't just about procedure, it's about building organizational capacity to detect and interrupt failure patterns. The integration, the standards requirements are not separate, independent items, okay? They are an integrated system designed to prevent failure patterns. First, to prevent pattern one, slow failure, HACCP, we need to integrate HACCP monitoring plus management review plus internal audit and plus trend analysis. To prevent pattern two, interface failure, we need to integrate supplier management plus communication plus traceability plus receiving controls. To prevent third patterns problem moving forward, we need to integrate non-conformance management plus product release plus corrective actions plus authority. To prevent pattern four, which is symbolic evidence, we need to integrate validation plus verification plus management review plus random checks. To prevent the fifth pattern, which is pressure wins, we need to integrate, uh, we need validation under to integrate validation under actual condition, plus resources management, plus contingency planning, plus design. The implementation principle here, when implementing standards requirements, ask the following question. First, which failure patterns does this requirement prevent? Secondly, how does this requirement detect warning signs? Third, what would happen if these requirements become symbolic? And fourth, does this requirement work under pressure? This transforms and standards from this transforms the standards from compliance checklists into symbolic failure prevention tools. The audit principle here, when auditing, internal or external, you should assess the following. First, does this requirement actually prevent the intended failure patterns? Secondly, are warning signs being detected and acted upon? Thirdly, has these requirements become symbolic? Fourthly, how does this control work under operational pressure? This transforms audit from documentation review into systematic or into system effectiveness assessment. The bottom line here, the standards are not arbitrary, they are systematic responses to how food safety actually fails. Implement them with understanding of the failure patterns, they prevent and they become powerful tools for systematic safety management. Implement them as compliance checklists, and they become symbolic evidence. Pattern 4 in action. Real world implementation. Let's explore building failure patterns resistant system together. Practical approach to design systems that interrupt failure patterns before they cause harm. The integration principle. Failure patterns doesn't occur in isolation. A system that prevents one pattern often prevents others. The goal is integrated design that address systematic vulnerabilities, not just individual hazards. Now, implementation checklist is as following. Phase one, assessment and prioritization. That will be will take a week or two. First, complete failure patterns assessment by doing the following. Use the assessment tool from earlier in this module. Identify which patterns pose greatest risk to your organization. Gather evidence, including incident history, audit findings, and staff feedback, and then prioritize based on risk severity and implementation feasibility. Secondly, map current system by doing the following. Document current control for critical process, then identify interface and handovers, then map information flows, then identify pressure point and peak period. Thirdly, analyze historical failures by doing the following. Review last 12 months of incidents, complaints, and near misses, then classify each by failure patterns, then identify recurring patterns, then determine which patterns your current system fails to detect. Fourthly, establish baseline metrics by doing the following. Document current performance level, then identify leading indicators for each pattern, then establish measurement systems, then set improvement targets. Now, in phase two, which is design interventions, and that can take around 3 weeks from week 3 to week 6. For pattern 1, the slow failure or normalization, first implement trend analysis by doing the following. Deploy SPC charts for critical control points, then establish statistical baselines, then create automated alert for concerning trends, then train staff on trend interpretation. Secondly, build external perspective by doing the following. Schedule quarterly review by external personnel, then implement new employees feedback program, then engage external auditors to identify normalized conditions, then compare current state to historical baselines and not current performance. Thirdly, create escalation protocols by doing the following. Define trigger points for investigation, then assign clear responsibilities, then establish timeline for responses, then ensure authority to act. So that's for pattern 1. For pattern 2, interface failure, first map and document the interfaces by doing the following. Identify every handover point, define critical information for each interface, assign interface ownership, and create interface management procedures. Secondly, implement transfer verification by doing the following. Design verification protocols for each interface, then create standardized documentation, then establish acceptance criteria, then train personnel on verification requirements. Thirdly, monitor interface performance doing the following. Track information completeness and accuracy, then measure response times, then identify problem interfaces, then implement improvement actions. Now for pattern 3, which is problem moving forward, first establish a stop authority by doing the following. Define who can stop production at each stage, then remove barriers to stopping problems, then create clear escalation paths, then protect personnel who stop problems from retaliation. Secondly, align incentives by doing the following. Reward problem detection, not just throughput. Then measure and recognize quality performance. Then remove penalties for stopping problems. then celebrate prevented failures. Thirdly, track problem movement by doing the following. Monitor where problems are caught versus where they should be caught. Then analyze rework and reprocessing rates. Then review customer complaints for internally detected issues. Then identify systematic gaps in problem detection. For the fourth evidence becoming symbol, the fourth pattern, first verify evidence validity by doing the following. Randomly verify records against reality, then confirm monitoring detection actual problems, then test whether corrective actions are effective, then ensure supplier documentation is accurate. Secondly, connect evidence to actions by doing the following. Establish clear triggers for actions based on evidence, then demonstrate how evidence drives decisions, then eliminate evidence collections that doesn't inform actions, then make evidence review meaningful, not ceremonial. Thirdly, audit evidence systems by doing the following. Review whether monitoring is meaningful, then assess whether verifications verifies reality, then confirm corrective actions are effective, then ensure management review drives improvement. For the fifth pattern, which is pressure wins, first design for pressure by doing the following. Identify controls that depend on human attention, then automate critical controls where possible, then build uh, redundancy for critical systems, then design procedures that work under pressure. Secondly, test under pressure by doing the following. Simulate peak operation conditions, then identify which controls fail first, then strengthen vulnerable controls, then verify system performance during actual peak periods. Thirdly, build capacity by doing the following. Ensure adequate resources for peak periods, then cross-train personnel for flexibility, then maintain equipment to prevent failure during critical times, then plan for contingencies. Phase 3, implementation, which will start from around week 7 to week 12. First, pilot the implementation by doing the following. Select one high priority pattern, then implement interventions in limited scope, then monitor effectiveness, then refine based on experience. Secondly, train personnel by doing the following. Explain failure patterns and why they matter, then train on new procedures and tools, then emphasize the why, not just the what. Then create champions who understand and support the approach. Thirdly, establish monitoring by doing the following. Implement metrics for each intervention, then create dashboards for visibility, then establish review frequency, then assign responsibility for monitoring. Fourth, create feedback loops by doing the following. Regular review for interventions effectiveness, then adjust based on performance, then documentation of lessons learned, then sharing of success and challenges. Now, phase 4, expansion and integration, and that would be from month 4 to month 6. First, expand the scope by doing the following. Apply successfully interventions more broadly, then address additional failure patterns, then integrate interventions across patterns, then scale to entire operations. Secondly, integrate with existing systems by doing the following. Connect to HACCP and food safety plans, then align with management review processes, then incorporate into internal audit programs, then link to continuous improvement initiatives. Thirdly, build organizational capacity by doing the following. Develop internal expertise in failure pattern recognition, then create training programs for new personnel, then establish communities of practices, then share knowledge across sites and divisions. Fourth, demonstrate values by doing the following. Document prevented failures, then calculate cost avoidance. First, document prevented failures, then document cost avoidance, then share success stories, then build support for continuous investment. Now, in phase 5, which is continuous improvement, and that will be ongoing, it's not a one-time project. First, monitor leading indicators by doing the following. Track metrics for each failure patterns, then identify emerging patterns early, then adjust interventions as needed, then maintain vigilance against normalizations. Secondly, learn from near misses by doing the following. First, investigate close calls, not just failure. Then classify by failure patterns. Then identify system weaknesses. And then implement preventive actions. Third, maintain external perspective by doing the following. Regular external audits, benchmarking against other operations, industry participations and learnings, and fresh perspective from new personnel. Fourth, evolve the system by doing the following. Update based on new understanding, adapt to changing operations, incorporate new technologies, share learning across the organizations. Critical success factors here. First, management commitment through the following to measure the success. Visible support from leadership, resources allocated appropriately, authority to make changes, and patience for system development. The second measurement of success is clear communication through the following. Explain why this matters, connect to business outcomes, celebrate success, and learn from setbacks. That measurement of success is practical focus through the following. We start with highest risk patterns, implement in manageable phases, demonstrate quick wins, and build momentum. The fourth element is integration, not addition. Build on existing systems. Don't create parallel bureaucracy. Simplify where possible and focus on effectiveness, not documentation. Fifth, sustained efforts. You can demonstrate the success through the following. This is not a project and this is a system, so it requires ongoing attention and must be maintained against normalization, and it should become part of how you operate. The common implementation challenge. The first challenge, you will hear things like, we don't have time for this. Your response, you don't have time not to do this, you can say. but failure are more expensive than prevention. The solution? Start small, demonstrate value, and build support. And you can show them also the price of failure and the values you are showing from building small. Second challenge, you will face something like our system is already certified. Respond to that claim, certification is necessary, but not sufficient. And these patterns occur in certified system as we all witness here. The solution to that, frame as enhancement, not replacement of existing systems. The third challenge you will face such as this is too complex. The response to that, failure patterns are complex too. Preventions require systematic approach. And the solution to that, implement in phases and build capability over time. The fourth challenge you will face such as staff resist change. Respond to that, explain why current approach is insufficient and show evidence of patterns. The solution to that involve staff in design, demonstrate value, and celebrate successes. Measuring success, short term from 3 to 6 months, include the following. Interventions implemented for priority patterns, metrics established and tracked, early warning signs detected and acted upon, staff trained and engaged. Medium term from 6 to 12 months, the measure of success include the following. Demonstrated prevention of failures, improved performance on leading indicators, reduced incidents and near misses, expanded the scope across operations, and the long-term measurement of success after 1 year include the following. Systematic detection and interruption of failure patterns, culture of proactive problem solving, continuous improvement in system performance, and recognized as industry leaders in food safety. The ultimate goal here, built on systems that doesn't just react to failure, but systematically prevent them by detecting and interrupting failure patterns before they cause harm. This requires understanding how food safety really fail, as what we demonstrated throughout this module, designing interventions that address root causes, and maintaining vigilance against normalization again. You now have knowledge and tools to build such a system. Module 4 will provide additional implementation guides and support. Let's summarize the 5 universal failure patterns. This module has provided both conceptual understanding and practical implementation guides for preventing the failure patterns that repeat across all modern food systems. First pattern, failure is always slow at first. We demonstrated the following. Catastrophic failure begin as comfort, not crisis. Normalizations makes gradual drift invisible to daily operators, and each day feels normal, but cumulative deterioration is catastrophic. The prevention here, trend analysis, external perspective, and comparison to historical baseline. The warning signs that you are experiencing the first pattern, there are recurring issues and phrases like it's always been like that and growing maintenance backlog also. The second pattern, which is control breaks at interface, we demonstrate the following. Most controls are designed for processes, but failure lives between them, and we provided the evidence. Handovers between people, systems, department, or companies create gaps. Both sides of interface may have strong controls while the interface has none. prevent the interface gaps, you need interface mapping and explicit ownership and transfer verification. The warning sign that you have interface risk include information gap, responsibility confusion, and communication failures. The third patterns, which is problem moving forward instead of being stopped. Stopping problems is harder than passing them forward. Economic incentives favor throughputs over quality. Each party passes problems to the next, ensuring they reach consumers. And we demonstrate that with evidence and real world examples. The prevention for problem moving forward instead being stopped include the following: clear stop authority, align incentives, and problem tracking. The warning signs that you have uh, the problem moving forward risk include increasing rework and phrases like customer will handle it and rising complaints. The fourth patterns, which is evidence becoming symbolic, evidence of controls becomes separated from actual control. Documentation exists but no longer reflects reality. Records are completed but not reviewed or acted upon. The prevention of evidence becoming symbolic include random verification, evidence to action linkage, and meaningful review. Warning signs that you have evidence becoming symbolic risk include focus on paperwork of reality and records that don't trigger actions. The fifth pattern, which is pressure always wins without design. Production pressure is inevitable in commercial operations. Weak design collapse under pressure and strong design observe it. Controls designed for ideal conditions fail under real world stress. To prevent that, you need to design for pressure, build redundancy, and automate critical control point. The warning sign that the risk of pressure is prevailing include performance degradation during peak and increasing expectations to pressures. The integration. These patterns don't occur in isolation. They interact and reinforce each other as through the following. Normalization, pattern 1, makes interface failure, pattern 2, invisible. Interface failure allows problems to move forward, pattern 3. Problem moving forward creates symbolic evidence, pattern 4. Pressure, pattern 4, pattern 5 accelerates all other patterns. The evidence base here, these patterns are not theoretical, they are documented in the following. As we discussed, the Jensen Farms Cantaloupe outbreak in 2011 with 33 deaths and equipment and facility issues documented before the outbreak. In the Peanut Corporation of America case in 2011 with 9 deaths, there were 12 positive salmonella tests that ignored over 2 years. In Bluebell Creamery's Listeria in 2005, which resulted in 3 deaths, the environmental monitoring showed escalating contamination, but it was ignored also. In coupled E. coli outbreaks in 2015 to 2016, which resulted in multiple incidents, supplier and handling gaps were documented. In 2024 recall surge of 241 FDA recall with 93% increase in foreign material contamination. Prepared food recall. Prepared food recall, highest category due to the interface's failure. The labeling error, leading case due to symbolic evidence. sorry, prepared food, in prepared food recall, the highest category there is due to multiple interfaces failure. And in labeling errors, the leading case due to symbolic evidence and seasonal peak where pressure reveals design weakness. You can now do the following. First, recognize patterns before they cause harm. You can identify warning signs early and interrupt patterns before catastrophic failure. Then you can design better systems and you understand that effective food systems requires the following. Systems systems designed for real-world conditions, controls that work under pressure, evidence that connects to reality, interfaces that are explicitly managed, and culture where problems are reported and acted upon. Then also you can implement practical solutions and you have a specific tools to do the following. Detecting slow failures through trend analysis, managing interfaces through explicit controls, stopping problems through clear authority, ensuring evidence remains meaningful, and build systems that observe pressure. Also, you can lead cultural change because you understand that the following blame prevents learning and weaknesses system, blame prevents learning and weakens systems, failure are predictable from warning signs, preventions require systematic design, not just good intentions, and certification is necessary but not sufficient. The uncomfortable truth here, most food safety failures are not the result of bad actors or incompetent workers. They are the result of predictable patterns that emerge from how modern food systems operate under commercial pressure. But the empowering truth is, if failure follows predictable patterns, they can be systematically prevented through better design, better detection, and better response to warning signs. Your responsibilities include the following. Apply this knowledge in your operations, share it with your teams, and design systems that interrupt failure patterns, maintain vigilance against normalization, and act on warning signs before they become catastrophes. The path forward from here, Module 4 will provide additional implementation guides connecting the failure patterns to specific standards, requirements, and organizational practices. But the foundation is now in place. You understand how food safety really fails and therefore how to prevent those failures systematically. The question is no longer, can we prevent this failure? The question is now, will we act on what we know now? Most of food safety failures were predictable, the warning signs were present, and they were simply tolerated. Module 2, closing reflection. Let's look at it together. We end this module with uh, one penetrating question that forces self-examination without any accusation. This question is, where is your system, where in your system are problems allowed to move forward instead of being stopped? This question forces honest assumptions because every system has an answer. The question is now whether the problems move forward. They do. The question, sorry again, the question again, the fundamental question that we asked were, where in your system are problems allowed to move forward instead of being stuck? Now, this question forces honest assessment because every system has an answer. The question is not whether the problem move forward because they do, but the question is now where, why, and what are you doing about it? Why this question matters? It reveals pattern 3, problems move forward, but also expose the other patterns as following. If problems move forward consistently, normalization has occurred. That's one. If problems move forward at interface, interface control is weak. That's pattern 2. If problems are documented but still move forward, evidence is simple. That's pattern 4. And if problems move forward under pressure, design is weak. That's pattern 5. How to answer this question honestly? First, follow the product. Trace your product from raw material, consumer. At each stage, ask the following question. What problems could occur here? How would we detect them? What would stop them from moving forward? And what would allow them to move forward also? Then follow the pressure. Identify your highest pressure period and ask the following questions. Which controls are most likely to fail under pressure? And which problems are most likely to be passed forward? And what makes stopping problems difficult during these periods? And then follow the incentives. Examine your reward and penalty systems and ask the following questions. What behavior do we actually reward? What behavior do we actually punish? Is it easier to stop problem or pass them forward? And who bears the cost of stopping versus passes the problem? 4. Then follow the history. Review your last 10 customer complaints or internal quality issues and ask the following questions. Where should each problem have been caught? Where was the actual where was it actually caught? What allows it to move forward? As these patterns repeated, the uncomfortable truth here, if you cannot answer this question, you don't understand your system well enough to prevent failure. If you can answer this question but haven't acted on it, you are accepting predictable failure. But the empowering truth is, once you can answer these questions honestly, you can design interventions. You can strengthen control where problems move forward. You can change incentives, and you can build authority to stop problems, and you can prevent the next failure. Your assignment before Module 4, answer the questions for your operations. Answer these questions for your operation. Be specific. Identify at least 3 places where problems are allowed to move forward, and for each place, identify the following. Why problems move forward instead of being stopped? Then, what warning signs would indicate this happening? Then, what would need to change to stop problem at this point? Module 4 will show you how to implement these changes systematically. Transition to Module 4 for understanding the prevention. If food safety failure allows predictable patterns, then preventions cannot be reactive. It must be systematic design and continuous. You will learn. You have learned in Module 3 the following: the 5 universal failure patterns that repeat across all food systems, why these patterns emerge even in certified and audited facilities, how normalizations makes dangerous conditions invisible, and why blame prevents learning and weakened systems. And the most failures are predictable from warning signs that existed months before catastrophe. The critical shift here that happened include from reacting to incidents to from there to detecting patterns before they cause harm. And then from blaming individual, the shift happened to designing systems that prevent failure. And from documenting compliance, the shift happened to verifying actual control. And from managing hazard, the shift happened to managing system performance. What's next in Module 4? You will cover those. How to design system that interrupt failure patterns and specific tools for your detecting warning signs early, and how standards requirements map to failure patterns prevention, and also building organization capacity for continuous improvement, and creating culture where problems are reported, not hidden. The promise: if you understand how food safety fail, you can design systems that prevent this failure. Module 4 will show you how. The module 3 is complete, and now you understand how food safety really fail. You have completed the most challenging module in the course, actually. You now understand something that many food safety professionals never grasp: how good intentions, documented procedures, and certified systems can still produce catastrophic failures. You have examined failure across the following. We have examined the failure across different sectors: meat, dairy, produce, nuts, spices, seafood, and confectionery. You have examined the failure across different regions, include USA, UK, New Zealand, France, and global supply chain. And also you have examined the failure across different scales, include small family operations to multinational corporations. And you have examined failure across different decades, from patterns that repeat themselves from 2006 and to 2024, and the companies differed. The hazard was different, but the failure patterns were identical. You can now do the following. First, recognize failure patterns before they cause harm. You can identify the warning signs of the following: slow failure and normalization, interface control gaps, problems moving forward instead of being stopped, evidence becoming symbolic, and system designs that cannot absorb pressure. You can now ask better questions. Instead of who failed, you can ask what patterns enabled this failure, what warning signs existed, why didn't our problem detect and act on these signs, how do we design systems that interrupt this pattern. Design stronger systems. You can understand that effective food safety requires the following: systems designed for real world conditions, not ideal conditions; controls that work under pressure, not just during audits; evidence that cannot connects to reality, not just documentation; interfaces that are explicitly managed, not assumed; cultures where problems are reported and acted upon. The uncomfortable truths you now accept: most food safety failures were not the results of bad actors or incompetent workers. They are the results of predictable patterns that emerge from how modern food systems operate under commercial pressure. The empowering truth you now possess is: if failure follows predictable pattern, they can be systematically prevented through better design, better detection, and better response to warning signs. Your responsibility, you cannot unknow what you know now and what you understand now after this module. You have a responsibility to apply this knowledge to your operations, to share it with your team, and to design systems that interpret failure patterns before they cause harm. Module 4 will show you exactly how to do that. Today, we completed 5 universal patterns, failure patterns that repeat across the industries, countries, and scale because they emerge from system design, not individual action. You have experienced zero blame required, understanding failure patterns as a system design issue, not discipline problem, enable effective prevention rather than punishment. And we have one critical question. When in your system are problems allowed to move forward instead of being stuck? Where? Thank you for today and see you in Module 4.